All right, sounds good. Well, good morning, everyone. Welcome to the Lunar Thermal Analysis Guidebook short course. You will be covering most of the sections in the guidebook within our allocated time. So we have 2 hours right now, then a lunch break, then we have another 2 hours afterwards. At the end of the course, we will be available to answer questions. If we have time, we can answer questions before our lunch break, so feel free to leave your questions in the chat box. Okay, so let's introduce our panelists. I'm Carlos Gomez, which I'm also today's moderator. I have been working at NASA Marshall Space Flight Center for about 12 years next Tuesday, actually. I graduated from the University of Texas, El Paso with a bachelor's and master's in mechanical engineering. I have provided thermal support for the heliophysics sounding rocket program and life support systems. I currently spend most of my time supporting Space Launch System and the Human Landing System. And I'm also the new chair for the Lunar Thermal Environment Task Team. All right, next up we have Callie McKelvey. She has been employed with the NASA Marshall Space Flight Center for over 15 years since graduating from the University of Alabama in Huntsville with a bachelor's in mechanical engineering. Callie has developed a variety of experiences in thermal analysis, system engineering, aerosciences, and life support systems while supporting a variety of projects and programs including the Constellation Program, Space Launch System, Mars Ascent Vehicle, Human Landing System, and the Volatiles Investigating Polar Exploration Rover. In short, that's a Viper. Callie currently serves as the branch chief at Marshall EV34 Thermal Analysis and Control Branch. Next, we have Greg Shunk. He has been employed with the NASA Marshall Space Flight Center for over 39 years since graduating with a Bachelor's of Mechanical Engineering from the Georgia Institute of Technology. He also earned a Master's of Science in Mechanical Engineering from the University of Alabama in Huntsville. Greg has provided thermal and fluid engineering support for many projects, including the International Space Station, Deep Space Habitation, and Chandra X-ray Observatory, Advanced Life Support Systems, and the Next Generation Space Telescope. He currently enjoys technology development and working on NASA's Moon to Mars program. Then we have Lisa Erickson. She's been employed with NASA Johnson Space Center since 2012, since graduating with a Bachelor's of Mechanical Engineering from the Valparaiso University. Lisa has provided thermal engineering support for various technology development projects related to active thermal control and lunar in situ resource utilization. For the past several years, Lisa has enjoyed supporting NASA's Human Landing System program. And last but not least, we have Brian Hamill. He has been with NASA Marshall Space Flight Center as a thermal engineer for 14 years. Brian graduated with a Bachelor's of Science in Mechanical Engineering and Mechanical and Aerospace Engineering from the University of Alabama in Huntsville. He has supported several programs such as the International Space Station, Space Launch System, and Human Landing System. Brian served as the chair of the Lunar Thermal Environment Task Team during its initial publication. So he's one of the originals actually who wrote the Thermal Analysis Guidebook with Lisa and Greg. He is now the Liquid Propulsion Thermal Design and Analysis Team Lead at Marshall Space Flight Center. So now I'll go ahead and pass it down to Callie. She'll kick off the introduction for this short course. Go ahead, Callie.
Okay, hey, thanks, Carlos. You still hear me okay?
Loud and clear.
Okay, perfect. All right, well, thanks for the introductions, Carlos, and we'll go ahead and jump right into our course today. I've just got 5 quick slides to kind of introduce some of the terms you're probably going to hear a lot throughout the course today, and then a little bit more about our agenda. So you've heard Carlos mention a Lunar Thermal Analysis Guidebook. In short, we call it the LTAG. So that is really the basis of this course today. It's just what it sounds like. It's a guidebook, and we're going to be stepping through different sections of the guidebook today, more with our analytical hat on and showing you how we would implement certain portions of the guidebook. So what is LTAG? LTAG is a document that was developed by the Lunar Thermal Environments Task Team over a course of about a year and a half, 2020, 2021 timeframe. The intent of the LTAG was to provide guidance to thermal analysts regarding how they do thermal analysis assessments of the lunar natural environments. When we first started thinking about this, the Disney document, which I'll talk about in a minute, has a lot of natural environments in it, and we wanted to make sure the analyst had an example and a clear understanding of how they would implement those environments and show that their design or their hardware was good to those environments. So we developed the LTAG in hopes to assist with that. Since the LTAG has been published, it's publicly available. Several questions have came in to the authors of the LTAG regarding implementation and certain analysis issues folks were having. So we thought it would be a good idea to bring this course to this audience and have it recorded. So hopefully folks can refer back to this as they have questions in the future. And then just to let them know that this is out there and that we're here if there's questions, anything we can help with. So LTAG was the first user's guide that was produced under the Human Landing System program, like I said, several years ago. The document number is HLS UG 001. So that's kind of cool that it was the first user guide in the HLS program. And as I mentioned, it's publicly available, and there's a link in this presentation. And once I get off the stage, I can post those links in the chat so you guys can access it easier too. Okay, so what is LTET, the Lunar Thermal Environments Task Team? So this kind of came about once HLS was announced and we were starting the program. There's two different branches at Marshall, obviously the thermal branch and then the natural environments branch. And we knew that the Disney document where the natural environments live didn't have anything in there for lunar surface or lunar orbital type environments. And that was going to be the first step of this new task team we had built, was to develop the environments in the Disney document. So that was the first task for the LTET. And then once we got across that hurdle, that's when our second objective was to create the LTAG document, which we're going to be talking through today. So LTET is a community of engineers, scientists, weather specialists from the Natural Environments Group. And we would meet on a weekly basis, sometimes bi-weekly, just talking through how we get to this mission of having these environments here for the team to use, for our prime contractors to use, for academia, anyone who's doing lunar thermal analysis to use. So the LTET was formed. We have representatives from several NASA centers: Marshall Space Flight Center, Johnson Space Center, Glenn Research Center, and JPL. And if there's any other NASA centers out there who are listening to this and you have experience with lunar surface and lunar orbital environments, we'd be happy to add you to our team. So please reach out to Carlos. As Carlos mentioned, he is the chairman for the LTET. Brian Hamill, who's also on our panel today, was the first chairman of the LTET. So we've got the first and the second chairman here with us today, and then Greg and Lisa, who are also on, were major contributors to the LTEG document and important members of our LTET team. Okay, and lastly, another term you've heard me mention is the Disney document. That is the design specification for natural environments, which is developed by Marshall Space Flight Center, our EV44 branch, which is our natural environments team. The Disney is not a new document. It's been around since I've been here for 15 years or so. It was originally developed under the Constellation program, the Ares program. And the purpose of the Disney is just kind of what it says. It develops terrestrial environments, both at launch sites for launch abort, normal landing sites. It includes winds, temps, pressures, lots of other things. And it newly has space environments in there for ionizing radiation, orbital debris, meteoroids, thermosphere density, Earth, solar, lunar emitted radiation, and even more. So it has all the environments that you would need to design your spacecraft, your vehicle, your payload, whatever you're working on, for the natural environments both of Earth and the Moon. And it has a placeholder in there for future natural environments for the Mars atmosphere and Mars surface. So eventually that will be the next hurdle that we go through, is adding that section to the Disney document. So like I said, Disney was developed under the Constellation program, and it's evolved over the years to support major programs like SLS, and now its main focus is the HLS program. The Disney document number is SLS Spec 159, and it's also publicly available. So I will put that link in the chat here shortly too. Okay, Our agenda and presenters for today, Carlos already introduced himself, Greg Shunt, Brian Hamill, and Lisa Erickson, all members of the LTED and all contributors to the LTAG document. Our short course today has 2 hours before lunch and 2 hours after lunch, and we're probably going to eat up every single second of that window. We've got a lot of content today, but we'll try to have some time for question and answer at the end. The presentations today, it's a combination of technical presentations about the environments and how we analyze them, and then we have some pre-recorded analysis demonstrations to play as well. The agenda for today, we're going to be talking about the Earth's moon, space and surface thermal environments, the properties of lunar regolith, how to model a lunar orbit, how to model a ground plane for the lunar surface, and we have a video demonstrating how you would do that in an analysis format. We'll be talking vectorless, shading and blockage, lunar surface 3D terrain modeling approaches, and we also have a video of how you would mesh a 3D terrain. And then we'll have a closeout summary. Our session today is not going to touch every single section of the LTED. We have the LTAG, so there's a few sections we didn't get to, but we're trying to cram as much in this 4-hour window that we have.
We're going to begin with today just an overview of the Earth's moon. I'm going to try to talk a little bit about the physical characteristics of the Earth's moon. The lunar highlights some of the lunar thermal environment, the moon's orbit about the Earth, mention perpetually shaded regions in Earthshine, and a little bit of historical perspective from the Apollo program. Hopefully this will kind of introduce some themes that you'll see throughout the course. And provide some background on some of the modeling techniques and environments that we'll present today. As observed from the Earth, the moon's surface is characterized by, I think if everyone that's looked up at the moon has noticed that it's characterized by large dark regions known as mare or plural maria, and lighter surfaces referred to as highlands. Owing to a greater iron oxide composition, the mare are not as reflective as the lunar highlands, and were so named by ancient astronomers who mistakenly interpreted the mare as oceans. The highlands represent the original crust of the moon, whereas the mare was formed from lava flows that ultimately froze into rocks, and a little bit different composition, and hence their darkness. Both the mare and highlands have been shattered and fragmented by the impact of many meteoroids, asteroids, and comets over millions and billions of years to create the regolith that we're familiar with today. The lunar surface is characterized by the layer of regolith of variable thickness, dependent upon location, as described in the Disney design specification for natural environments, with the general composition provided below. It's interesting to note that oxygen, which is locked into all of the compounds listed below, is the most abundant element on the lunar surface, and silicon, I believe, is the second most abundant element. One of the most prominent features, as everyone knows, is our lunar craters. The Disney also provides a description of the crater size and frequency distribution, and the topography, the depth to diameter ratios for lunar craters. I wanted to point out, this may be useful for various projects that people are working on. There's details for craters near a specified landing site may be found in the Lunar Impact Crater Database, available at the link shown there. Over 8,700 craters are cataloged in the database with up to 80 parameters, including depth, diameter, location, which are identified for each crater. I went ahead and took that database and plotted, made a summary plot of the elevation angle derived from the crater depth over radius, versus the crater diameter for each crater shown. And I was kind of surprised to see how the craters fell on top of each other with the trends shown. The shape varies a little bit with size. The smallest craters, less than 10 kilometers, have a bowl shape, whereas the slightly larger craters are unable to maintain that shape due to the steepness of the wall, and the material flows down into the crater and the regolith falls toward the center. The largest craters have terraced walls and central peaks, but if you were, as I indicated, if you were trying to find a particular crater or try to design a mission in general for a particular size crater, this would be a good source to look at. And of course, some of the larger craters have a rim that might be attractive for exploration missions. So as we see at Shackleton, where there's a rim where you can, where there would be a place to place an asset on the lunar surface and maintain have nearly constant sunshine or constant illumination. Due to the rotational period of the moon, the thermophysical properties of the lunar regolith in the absence of an atmosphere, the moon's surface thermal environment is much more severe than a planet with an atmosphere, such as the Earth. The severity is both in magnitude and variation. Surface temperatures on the sunlit side of the moon can exceed 390 Kelvin. At the subsolar point, you see the bullseye there, where the middle of that would be the subsolar point where the sun is almost directly overhead. Dark side temperatures may plunge well below 90 Kelvin, and actually maybe 70 Kelvin, and then perpetually shaded regions would be even well below that. The performance of conventional spacecraft thermal control systems may be compromised or even rendered non-functional in the extreme environments. And really, there's been several papers written on it. Spacecraft in low lunar orbits passing directly above or near the subsolar point must account for the impacts of the infrared flux on the spacecraft. We've seen some solutions with attitude changes, or maybe even having a sublimator to augment heat rejection to reject the extra flux that's incident upon the spacecraft. I'm showing the plot there. I'm showing to the left is actually a thermal model of the entire lunar surface with the subsurface model, the transient thermal model. We have some empirical relations that we're going to show later on in the thermal environment section that are tied to measured data, but this is a good the model's a good approximation of what the temperature distribution looks like. Heat rejection on the lunar surface with lunar equatorial temperatures possibly exceeding 250 F, 250 degrees Fahrenheit. The high infrared background radiation from the lunar terrain and the surface can seriously compromise the performance of conventional thermal radiators at the low latitudes or near the equator or near the subsolar point. I show a plot here of normalized irradiance, and I break it up into three wave bands. The normalized irradiance is the irradiance for a particular temperature divided by the peak irradiance according to Wien's law. So the sun, as we know, can be approximated by a black body radiating at about 5,800 Kelvin. The equatorial band shown is for a background temperature of 390 Kelvin, and then the radiator is 283 Kelvin or 50 F. The solar spectrum is well separated from the radiator emission, but you can see that the lunar background radiation red and the will greatly reduce the energy a thermal radiator blue can emit due to the way the two overlap. At above about 8 microns, anything, if the radiator is designed to emit anything up at 283 Kelvin, anything up to about 8 microns, it would also absorb the background radiation from the surrounding high temperature regolith. The Apollo missions were severely constrained by the lunar thermal environment, resulting in restrictions in both duration and landing time of day. The lunar roving vehicle battery overheating was an issue on both Apollo 16 and 17 due to the local thermal environment and lunar dust accumulation on the LRV radiator. The way the wave bands are separated, we can deal with the solar. Obviously, as a conventional radiator, we can have a low solar absorbance and a high infrared emittance. But in the lunar environment, we have to use special provisions to account for the background infrared emittance, which overlaps with what we want, the temperature we want to radiate at. The orbital relationship between the Earth, Moon, and Sun is I've illustrated that below. Like many planetary satellites in the solar system, the Moon is tidally locked to the Earth, so that the rotational period is essentially the same as the orbital period about the Earth. And aside from small deviations due to libration, one side of the Moon always faces the Earth. The Moon's axis of rotation is tilted about 1.5 degrees relative to the ecliptic plane, and the lunar orbit plane is inclined 5.1 degrees relative to the ecliptic plane. So the lunar obliquity, inclination to the orbit plane, is the sum of those two angles, or about 6.7 degrees. The maximum sun elevation at the poles is related to the tilt, and the locations at the lunar poles of sufficient altitude, as I mentioned before, may experience near continuous sunlight. I'll just mention this drawing isn't exactly to scale. It shows the Earth and the Moon tilted about the same relative to the ecliptic plane, but of course the Moon is only tilted a degree and a half, whereas the Earth is tilted about 23 and a half degrees relative to the ecliptic plane. I might mention a few things about a few facets about our libration. That's the apparent wobbling of the Moon as observed from the Earth. If you look at the Moon, you would in photograph it over time, you would notice a wobbling or kind of shifting of the Moon. There are three types of libration. There's longitudinal, latitude, and diurnal. The longitudinal libration is really what we're most interested in, and it results from the change in speed of the Moon over its slightly elliptical orbit about the Earth. As you see up above there, the perigee is less than the apogee, and the orbit is slightly eccentric. So the Moon changes speeds, and that affects the how the Moon is tidally locked to the Earth, the changing in speeds. So you would notice a little bit longitudinally. You'd notice a little bit of a side-to-side wobble of the Moon over the lunar day. The latitude is due to the variation in tilt, and that's just basically due to the orbit as the Moon either tilts to or from the Earth. That you would notice a latitude libration. And diurnal is just the change in the position of the observer on the Earth. If you're observing the Moon over an Earth day, you would notice a perspective, a change in perspective of the Moon. I believe that's called parallax, and that doesn't really concern us too much from a thermal standpoint. That's more of an optical type of effect. The lunar orbital period of the Moon can be characterized relative to both a fixed point in space, sidereal, and to the Sun, synodic. The sidereal period is on the order of 27.3 days, while the synodic period is on the order of 29.5 days. The synodic period of 29.5 days represents sunrise to sunrise for a reference point on the surface of the Moon, as well as as a new moon to a new moon is viewed from the Earth. The sidereal period is really the time that it takes for the moon to rotate 360 degrees about the Earth. But due to the motion of the Earth at 300, after it's rotated 360 degrees, it isn't lined up exactly to where it started, and it has to continue on its path. And to actually be lined up back to where it started relative to the sun, that's the synodic period. And then the sidereal period is the time it takes for the moon to rotate, to complete one rotation about the Earth. For an asset on the lunar surface, I think the sun angle, or the sun angle, is periodic over the synodic period, and I think that would maybe be more pertinent for thermal assessments. A lot of times we derive or the lunar night that we see at the equator of approximately 14.25 days is due to the synodic period, because that's the sunrise and sunset is due to the moon's relationship to the sun. I should mention, I didn't get to put it in the presentation, but at the poles, more due to terrain effects, we can actually have a lunar night also, but it may be on the order of 100 hours or to 150 hours, possibly more, depending where you're at. And that's if we're at an optimum location with the position where we can have nearly continuous sunlight. We still may experience 100 hours of nighttime at the poles. So of course, the Survive the Night challenge for an equatorial low latitude mission is very significant at 14.5 days, or 14.25 days. But we also experience a lesser phenomenon at the poles, where we have to be able to design for a lunar night on the order of 100, 150 hours, depending on location. This is a plot of the solar elevation angle for South Pole locations, and I should mention, this is the first introduction of it. This is derived from the JPL Horizons application, which is an online ephemeris, and it's very useful for a lot of what we a lot of the orbital assessments we do to be able to provide a vector list that describes the position of the sun or any other target body relative to a location on the surface of the moon. You can see the lunar the monthly variation evident in the plots of the solar elevation angle for positions away from the poles at 89 or 85 degrees. And then if you're directly on the pole, you'll not see the synodic month is not quite as evident. I've shown the solar elevation angle with twilight, daytime, and nighttime noted. Daytime is with the sun completely above, would be with the sun completely above the horizon. Twilight, since the sun has an angular diameter of about 0.53 degrees, the sun can partially set above or below the horizon, and so that's what the twilight indicates. Below about a negative elevation angle of negative 0.53 degrees, the sun would be completely below the horizon, and then or completely above on the other side, and then of course completely below the horizon we would be at nighttime. The moon's tilt is evident with the lunar obliquity to the ecliptic approximates the peak solar elevation angle when you're directly at the pole. If you're away from the pole, you add the difference between 90 degrees and the latitude, and that would give you the peak elevation angle away from the pole. This is a similar plot for the solar elevation in the southern hemisphere. I don't really show the twilight period because the lunar tilt is really much smaller compared to the elevation angles at lower latitudes. You can see that the 4 at 0 degrees south latitude that we essentially approach a solar elevation angle of plus or minus 90 degrees. I believe the difference there is a little bit due to the tilt. So we don't actually see 90 degrees, exactly 90 degrees, but you can see some variation, especially at the nighttime solar elevation angle down as it approaches negative 90 degrees, but it varies a little bit. And then, of course, the elevation decreases with increasing latitude. I just had a quick note on the solar elevation angle relative to using the ephemeris. That this one may have gone better in one of the analysis sections, but I thought I would mention it here. As I indicated before, the JPL Horizons application computes the local solar elevation angle on the lunar surface relative to the center of the sun. For a perfectly collimated beam, the maximum elevation angle at the poles would be equal to the lunar obliquity relative to the ecliptic or the tilt. But the peak elevation angles computed by the ephemeris, you would notice, are maybe slightly different, on the order of 1.54 degrees plus or minus 0.014 degrees. The small difference is due to the sun-centered calculation and the lunar orbit inclination, but it's not really of consequence thermally. But just thought I would point that out. If you're thinking about a perfectly collimated beam, it's going to be slightly off if you compute the beam as if it were originated from the sun center, because there'll be a slight angle there that's either subtracted or added to a perfectly collimated beam. I believe that some of the differences you might see in the ephemeris data are also due to libration too. Could potentially be due to libration. So if you see, you may see it if you compute a solar elevation trajectory at the poles, you may notice it being a little bit different than the tilt relative to the or the lunar obliquity relative to the ecliptic. So those are the reasons why. I was going to describe a lunar seasons. Since the moon is tilted 1.5 degrees relative to the ecliptic, we do see a kind of a seasonal variation. That may be a bit of a misnomer. I've seen some authors indicate that the moon doesn't have seasons, but that's if we interpret them the same way as we do on the Earth, which wouldn't be accurate. We don't see a season on the moon at the same time each year, and then over the surface, most of the surface of the moon, the seasonal variation wouldn't really be apparent. But at the poles, the moon's tilt relative to the ecliptic can induce a seasonal type variation in both illumination and temperature. So that's kind of how we're using that nomenclature here. Of course, if you're at the equator and the moon is tilted plus or minus 1.5 degrees, you wouldn't really notice much of a difference or any sort of seasonal variation. As I mentioned before, at sufficient altitude, locations at either pole may experience near continuous illumination. So if you're elevated above the surface of the moon and tilted away from the sun, you still may be high enough to see illumination or see the sun. And then, of course, importantly, portions of polar craters may remain perpetually shadowed, and that has been detected. There may be frozen water in those craters, and that's the interest there. For perpetually shaded regions, detailed thermal analysis using the thermophysical properties of the lunar surface and subsurface with the ground heat flow that result in surface temperature predictions approaching as low as 18 Kelvin for regions that are considered to be permanently shaded. But the floor of the craters near the lunar poles can experience reflected solar flux from the crater walls, which can increase the surface temperature to approximately 50 Kelvin, even without direct solar flux impingement. And then there also may be contributions from Earth albedo and re-radiation. It may be a factor too from the sidewalls. But it's quite possible that we see regions in perpetually shaded regions in the craters that are in the 20 to 30 Kelvin range. They're of particular interest due to the presence of frozen water. It's believed that the ice in the craters came from comets that impacted the moon over the last 2 to 3 billion years. What's really unique about frozen water craters is that at the very low pressure of the tenuous lunar atmosphere, I believe it's I don't remember exactly. I believe it's on 10 to the negative 10th torr or 10 to the negative 12th torr, something like that. At those very low pressures, many volatiles don't sublimate significantly at temperatures in the 20 to 30 K range. So you can have ice and other constituents survive in the craters based on whatever may have been deposited there by the comets. I was also just going to briefly mention Earthshine. Perpetually shaded regions of the lunar poles may experience non-negligible thermal radiation and reflected solar radiance from the Earth. Some authors have indicated that the peak broadband Earthshine may exceed 150 milliwatts per square meter for localized regions. That isn't significant over most of the surface of the moon, but when you're talking about temperatures at these very low temperatures in the craters, that could be a significant heat input. A typical yearly variation of the Earthshine is shown for a location at an 85-degree north latitude with a surface tilt of 15 degrees. This was calculated, and I'm going to, when we go through the orbital vector list in a later presentation, I'm just going to briefly show how this was calculated, but just wanted to introduce it here. The calculation I did was only about the total between the infrared contribution from the Earth and the solar, which is reflected solar from the Earth. Is only about half of the 150 milliwatts per square meter in this case, but depending on the time of year and the location, it could vary. In the plot below, the flux from the Earth would be zero when the Earth sets below the horizon, and the variation of the reflected solar albedo from the Earth are greater than the infrared contribution. But this is along with I'm going to mention the internal ground flux coming up here shortly, and that along with the Earthshine may contribute to the behavior of the permanently shadowed regions. Okay, I was going to do kind of just a brief overview of the Apollo missions and how that affects some of our assessments we do thermally. There were 6 Apollo missions that landed on the surface of the moon. They all landed at a latitude that was less than 26 degrees north or within, I should say, within 26 degrees of the equator. There were several southern locations south of the equator and then several locations north of the equator. The duration ranged from 22 to 75 hours for the missions. They got increasingly longer with the later missions. I went back to the ephemeris, and given the location and the dates, I calculated the peak sun angle. For all the missions, the sun was rising over the mission, so they landed in sunlight, and then the sun was rising. It turns out at these sun angles, all the Apollo missions, they landed essentially in the mid-morning, early morning, or mid-morning time frame relative to the lunar day. None of them really landed at near a solar noon. And I just based upon a simple energy balance, estimated the surface temperature at each location, and they were relatively moderate, although getting up for Apollo 16, it was starting to get kind of warm by the time potentially warm by the time they left. The Apollo lunar module thermal control system is interesting. The waste heat rejection was achieved via water evaporation or sublimation from onboard stores. The onboard water supply consisted of one 367-pound tank in the descent stage and two smaller tanks in the ascent stage. The cooling water was consumed for drinking as well. This would result in severe restrictions on mission duration as well as constraints on the landing time and location. So they didn't actually use a radiator as we know it to reject heat, but sublimated water from onboard storage, even at the somewhat reduced temperatures that they experienced, which weren't at the subsolar point. For the Apollo, the Lunar Rover thermal management, the thermal control systems consisted of several passive approaches: special surface finishes, multi-layer insulation, space radiators, second surface mirrors, and thermal straps and heat sinks. It was discovered as the rover traversed the surface that lunar dust and was readily distributed during normal operations in and around the rover, with a solar absorbance of potentially greater than 0.9. I think some of the data we'll show later is maybe in the 0.8 to 0.9 range for normal solar absorbance. The accumulated lunar dust greatly hindered the radiator surfaces. Excuse me, on Apollo 16 and 17, the LRV batteries experienced problems with overheating due to dust accumulation on the radiators, and that prompted John Young to remark that dust is the #1 concern in returning to the moon. And we don't specifically talk a lot about dust in the course, but that's always something that's in the back should be in the back of your mind when designing thermal control systems for lunar surface applications. Surveyor III was an unmanned probe launched in 1967, and it remained exposed to the lunar environment for 31 months prior to the arrival of Apollo 12. They landed Apollo 12 near approximately 160 meters from Surveyor's location. You can kind of see, it's kind of an interesting picture below, where you see the lunar module parked on the ridge just beyond Surveyor. Several artifacts from Surveyor were recovered and returned to Earth. One interesting discovery was the appearance of a number of microscopic craters, and it was conjectured that, well, some were on the side facing the lunar module, and it was speculated that the craters resulted from lunar dust kicked up by the exhaust plume during landing. So again, dust is playing a factor. One final important measurement from Apollo was the Apollo Lunar Surface Experiment Package, where the astronauts were able to insert a probe several meters into the lunar surface and measure temperature and heat flow. The heat flow experiment found that the surface layer temperature during the night was 760 Kelvin, and it was rising to a maximum of 358 Kelvin during the day. And this would have been at the locations for the Apollo 16 and 17 landing site. The temperature at 1.5 meters under the surface was found to be a constant 253 Kelvin, indicating that the regolith is an excellent thermal insulator. The offset measurements were taken for several years after the Apollo astronauts left and after the mission was completed. And I believe that telemetry data is available at the link below. If you go to the Honeysuckle Creek site, you can see the temperature variation of the surface and underneath the surface as measured by offset, or the two offset measurements. The results of these measurements also indicated a heat flow of 21 milliwatts per square meter at the Apollo 15 landing site and 16 milliwatts per square meter at the Apollo 17 landing site. So we have this kind of background heat flow from the interior of the moon flowing out to the surface. Now, I don't believe that we necessarily know what that heat flow is at the poles, but this was at a more equatorial location. And Carlos, I think that concludes my presentation for today on the Earth's moon.
Thanks, Greg. Now we'll go ahead and start with Brian.
All right, so real quick, mic check, and can you see the screen?
You sound loud and clear, and I'm still waiting for your screen to pop up.
Okay.
There we go.
All right. And full screen. Okay, so I'm going to talk about the lunar space and surface thermal environments. It's just kind of a Cliff Notes or 101 level walkthrough of the environment content inside the LTAG, or how you would derive them to put into a thermal model. The sources, of course, is Disney and the LTAG. Just real quick, the LTAG was considered to be or built to be a companion document to Disney. I think one thing that has not been said today is that the environments in Disney are the design to environments. Sometimes they will rev that document. Maybe the LTAG doesn't have the latest values. Any values used in the LTAG are really meant as examples of reference when we ought to be referring directly back to the Disney. The Disney environments are inputs for both orbital or surface analyses. Lunar surface albedo and planet shine values can be characterized for our orbital cases. And one thing to note is when you have a landed vehicle or surface asset, you need to have a participatory element model ground plane because without an atmosphere, the shadowing of your vehicle or landed asset does cause a really coupled thermal interaction between the surface and the vehicle, as opposed to using just either an idealized ground plane or standard boundary condition temperature. So one of the first environment we want to talk about here is solar flux. This is a separate range within Disney for lunar space, and it accounts for the additional variation in the moon-sun distance as the moon orbits the Earth, and should not be confused with a solar range that's provided for near-Earth mission phases. Disney gives a mean, a max, and a min solar flux depending upon the distance of the moon from the sun. Here it's listed, 1421 as a max, all the way to 1315 watts per square meter as a minimum. One important thing to note is there is a statement in the Disney that these values should include an additional 5 watts per meter squared measurement uncertainty when you're using it for thermal analysis. That's just the measurements that were taken by the orbital asset. That's the uncertainty in the instrumentation, so we need to add that in. So if you're in a thermal model, it's 1426 or 1310 as a minimum. The mean, of course, just use the mean. So the other ones given, albedo, as Greg mentioned, it was suspected that it could be up and higher than 0.9. So, or the absorptivity, right, the emissivity. So that corresponds with an albedo of 0.07. That would put the absorptivity of the regolith at 1 minus the albedo. An average is for the Earth facing. These were taken by Lunar Reconnaissance Orbiter, I think. Just a lot of measurements as that was doing its mission. So it found an average on the Earth facing side was 0.12. With a local high of 0.2 and a local low of 0.7. Lunar far side, again, average was 0.15, high of, again, 0.2, and the low there of 0.1. Emissivity was found to be a range between 0.95 and 0.98. For orbital cases, well, I'll get to that in another slide, sorry. So another thing that we need to know is planet shine derivation. So their absorptivity, this will give us it's 1 minus the albedo, and that can give us a planet shine. So at the subsolar point, you have this equation here, Stefan Boltzmann, the emissivity of the regolith, and of course the surface temperature to the fourth is approximately equal to the absorptivity times the solar constant. Now that solar irradiance on the surface, it varies as a function of the solar incidence angle. So, the angle between the sun moon vector and moon, your satellite that's in orbit. So this here is the solar, what the surface or the solar irradiance would be onto your spacecraft if you were to do, say, a solar vector type orbit, where you would calculate the solar irradiance, or solar incidence angle from the sun to the moon to your spacecraft. One thing to note, obviously solar irradiance, or your solar constant would be times the incident angle would be 0 on the unilluminated surface. So, but it's not that would tend to give you a surface temperature of your background radiation space. So to account for that, Disney does state that the measured unilluminated surface temperature is 100 Kelvin plus or minus 20. So how would you put that into a thermal model, say thermal desktop, where you have a planetary representation? So here Disney says, hey, you can modify that equation to account for the discontinuity across the illuminated terminator. So there, solar incidence angle of 90 degrees. So for planetary coordinate system, there's two options here. We'll go ahead and talk about planetary coordinate system. I typically don't recommend that when I'm talking to people. It's just a much more complex calculation. And so the QIR of any point on the surface on the planetary coordinate system as the cosine of the longitude on the planet of a particular location minus the where the subsolar point is at that point in time, times the latitude of both of those, and then of course the calculation for QAR at the subsolar point. Here we take into account the dark side illumination, or dark side temperature, if you would, or unilluminated side temperature, as the solar incidence angle or approaches 9, or I guess the difference between subsolar and the point on the planet, right? So getting closer to the terminator. As you get close to the terminator, this whole term goes to 0 and it becomes just the unilluminated QIR. But as you approach the subsolar point, this term here actually begins to diminish, or the combined term. This becomes equal to the full, and this cancels itself out. And so that's how we take into account that discontinuity over the terminator. And you can have just an else, where if the planet is greater than that, then, or the difference in the two coordinates is greater than 90, you just use the unilluminated flux. The much easier version, is the subsolar coordinate system that Thermal Desktop allows you to use. Here you're just taking the difference in a latitude, if you would. It's just one direction away from the subsolar point. And you're using the same sort of unilluminated compensation across the discontinuity. And it's very much, it's a lot easier. Here I have listed all of the different constants that are used in these derivations. What that ends up looking like, we'll start over here on the right-hand side of the screen, is this would be an input to Thermal Desktop, the first image, if you were using the planetary coordinate system. And this is something you almost have to recalculate for any given orbit parameter, depending upon the seasonal change or right ascension of ascending node, because the planetary coordinate system is fixed in time. So, and the subsolar point does change. Here, for if you were to use the subsolar inputs, I included a 0 column. You can get by with just the minus 180 and a 180. It's a simpler input, and the software will orient your subsolar IR point, right, with the subsolar solar point, so you don't have a disagreement there in vector. The other thing that we have included in LTAG is sort of a real basic summary of, if you're running a cold case, well, what values do I use? Because there's a whole bunch of different values in the document, min, max. For albedo and emissivity, there's different ranges. So what's the, real basic, what do you do? So if you are sensitive in a solar spectrum, so your optical properties of your spacecraft. We would recommend, you use albedo and emissivity listed here with a low solar constant, and this will give you a cold case. Again, also if you're real sensitive in your standard infrared emissivity band, these would be the values we suggest that you use. And then of course there's a combined case with an unilluminated surface temperature of 80. And then of course there's the hot case values where it's kind of inverted, where again, if you're sensitive to albedo band, electromagnetic radiation or IR band, these would be the values we would recommend to use for an enveloping case. So this is biasing it according to the optical properties of your spacecraft. So this is in LTAG. This is something that I pass out a lot to people who are asking me, well, what do I use? So this is real basic summary of the environments to apply in a thermal model. Again, going back to the discussion between using a planetary or a subsolar coordinate system. Again, I recommend using a subsolar coordinate system. Again, simpler input, easier equation. But also there's a very easy to make error when you're making a model if you're not careful. Since the solar heat rates are calculated during, a RAD-K heat rate task, and you're calculating the planetary surface temperatures or the flux coming from the planet in a separate sort of out of model calculation, that table may not align with your orbital parameters. Like I said, right ascension of sun, the ascending node, and the others. So you can end up with an environment kind of like B here on the right, where the hot IR point of your planet is actually on the terminator, or any number of potential off points, where the solar vector is sitting there, pointing to the sun as RadCAD would do, but you just have the wrong surface temperatures of the planet underneath it. So using the solar or subsolar coordinate system will always get you the image on the right, where it's always aligned. And so it's one of the things that I try to recommend to people as I'm talking through this analysis. So another thing we want to talk about is solar eclipse durations. In low lunar orbit, these are of course in Disney. As the moon would pass behind the Earth and the sun would become occluded, if you're a spacecraft in low lunar orbit, you can also expect to not have solar illumination. So Disney provides at different orbital altitudes the worst case expected no solar flux for a lunar eclipse. So they vary, of course, as you get the totality is less the higher you get, but the no solar flux worst case, I guess you spend further behind the moon as it's you're actually a slower orbit. Here in this image off to the right, these are measurements taken. These are Earth-based measurements taken during a lunar eclipse of various points on the Earth side, face of the moon, of temperature during an eclipse of 1971. And you can see that the surface temperatures react very quickly. Kind of almost looks like the surface temperature plots, the lunar day surface temperature plots. Of course, it's over a much shorter time span of a lunar eclipse. So looking at this data, looking at the no solar flux data given in Disney, we recommend that when you're modeling an eclipse event, set solar albedo to 0 for the duration of the partial and total eclipse. Planet shine should be set to, or can be set easily to, the unilluminated side values. It's warmer, right? Instead of being 120 or between 120 and 80, here these surface temperatures are closer to 160, 170. But again, you're enveloping. It's a short time. You're trying to see again if the surface asset or the orbital asset that you have can survive the duration. And you can envelope it, and that's if you can survive that, then you don't need to sharpen the pencil anymore. And again, lunar shadow as you just go behind the moon. just normal shadowing calculated by orbital parameters represents your worst case. For the HLS program, the NRHO orbit is much discussed. So there were calculations by Johnson Space Center that show that the Plan 9.2 NRHO is able to avoid eclipse by Earth shadow for the most part, everywhere from 2020 to 2035. There's 2 partial eclipses in the 14th and 15th year, but their report said that minor orbital adjustments by the spacecraft could actually avoid those as well. So we're gonna, you can assume that if you're in an NRHO, that you can avoid that Earth shadow lunar eclipse. However, lunar shadow, just going behind the moon, that occurs several times, but it's always less than 80 minutes. There's a Gateway Integrated Thermal Model document that provides a table that we've also listed in the LTAG that gives umbra and misspelled, sorry, maximum and minimum values for your orbital shadow time in an NRHO. Depending upon how you're simulating an NRHO, normal shadowing by the moon calculated by software may not represent the worst case, but values from the table there should be used. I've managed to get using just standard orbit simulation about 70 minutes. So if we consider that to be close enough to worst case, or you can also just force the solar illumination to be off for another couple minutes. So real basic slide. If you start modeling on the surface, you would use the same solar flux values listed in Disney. Some of the surface features, Greg mentioned this. There's a whole catalog of craters. We've got to worry about shadowing both of our vehicle on the surface as well as any sort of local terrain features. So there was that catalog of crater features that Greg had in his presentation. Disney also defines typical geometries for craters that are smaller, like 10 to 15 kilometers in diameter. And you can use those equations and characterizations to represent a very simplistic crater. They tend to be more symmetrical. So larger craters, of course, aren't characterized in Disney, and you can use measured lunar topography or like Greg's reference. Boulders and other large object distributions are defined in Disney. I'm not going to go over them here, but those can be used to populate nearby surface feature effects. So say, you have a boulder that's illuminated and it's on the otherwise shadowed side of your surface asset. That could be important to include. So the surface temperature. So the landing site optical properties, you can assume that it's bounded by the min and max values and emissivities, albedo and emissivities from Disney. But if you need a more detailed surface representation, so you want to sharpen that pencil, there are lots of sources for a very high fidelity site-specific optical property source. So they're here. This would be much further along in an analysis than final stages of a program, but you can use this for very high fidelity analysis if that's what you so choose, or you can try to do a bounding analysis with what's provided in the tables earlier and also in Disney. So there's a steady state approximation to lunar surface temperature that we used a lot in our analysis. So the surface temperatures are a function of direct sunlight, reflected and nearby surfaces. And you also have subsurface heat flow. Greg mentioned that earlier. We've also talked about the dark side surface or unilluminated side surface. It's about 100 Kelvin. That's about 5 watts per meter squared. That's being re-radiated out of the surface. So you would need to compensate for that when you're doing the steady state approximation here. So we assume that has very low thermal conductivity and the surface temperatures are particularly sensitive to shading. So a lot of times we will just treat, or you can treat in a very simplistic model, your ground plane that you're including in the model as almost an arithmetic surface. Again, that's a very simplistic representation, and you can go into much more depth with into the surface conductivities and then thermal capacitance of the regolith. But given the time scales involved for a whole lunar day, this would be more of an enveloping case. Here you can see Apollo 17 measured data versus the steady state approximation temperature curve there for the surface. And that's an equatorial. So, daytime surface temperatures, we're saying, can be approximated by just the energy balance on the surface. I don't want to spend too much time. Greg addressed a lot of this in his presentation, but ground heat flow is an important parameter for determining the surfaces, especially at polar regions, because their magnitude starts becoming more significant compared to what you get from other sources. Again, Greg also mentioned the effect of Earthshine on the perpetually shaded regions. So since that's already been addressed, I'm just going to go to the next slide. Well, that's the end. So Carlos, I think I'm done.
Yes, you are, sir. Thank you very much. And now we'll jump in with Greg.
Okay. Hopefully everyone can see and hear me okay. The next section is thermophysical and optical properties of lunar regolith. And I'm going to be presenting this along with Lisa Erickson. I'm going to start off and have a few slides on optical properties, and then Lisa is going to discuss thermo physical properties of lunar regolith. Just as a little bit of background, this is contained in the LTAG. I won't dwell on this too much, but I think everyone's probably familiar with for radiation heat transfer. The electromagnetic spectrum is subdivided into multiple bands. We're primarily interested in the thermal radiation band between 0.1 and 100 microns in wavelength. Below 0.1 microns, the electromagnetic energy it can pass through objects, and then above 100 microns, it has very little heat energy under practical conditions. The one exception may be extremely low temperatures, such as on the far side of the moon or perpetually shaded craters. We might be interested in heat transfer beyond 100 microns. The thermal analyses are typically conducted using a two-wave band absorptance model, which everyone's familiar with. We subdivide into the thermal energy spectrum into solar and infrared, and with the threshold at 3 microns generally, or about 3 microns, and so that's what a lot of the further discussion is based on. For solar absorptivity and albedo is the fraction of incident light or solar radiation reflected by a surface, and may be defined in several different ways. Normal albedo is the reflectance of a surface when both viewed and illuminated in the local vertical direction. So you can see the three slides below on the bottom left is normal albedo. A directional hemispherical albedo is the reflectance in all directions resulting from direct illumination from a specific direction. So the illumination direction is defined by the theta angle, and then you can integrate the reflectance over the delta, over a range delta. If you're looking at the total hemispherical albedo, you would integrate that from 0 to pi. I'm sorry, and the way this is oriented, it would be from negative pi over 2 to pi over 2, the way delta is defined below. And then for total hemispherical albedo is the reflectance in all viewing directions integrated over all phase angles. The bolometric albedos are obtained by integrating the wavelength-dependent albedo over the wave band of interest, as illustrated below for the lunar surface normal and hemispherical albedos A bolometric or hemispherical albedo would be averaged against the solar spectrum, and that's represented by a black body radiating at 5800 Kelvin. And that's the E sub B term in the equations below, given as a function of temperature, which would be 5800 Kelvin, and then the dependence on lambda or wavelength. And then the total emission would be the sigma t to the fourth in the denominator. The hemispherical bolometric albedo is computed in 2 steps. It's first integrated over a wavelength for a specific direction, and then integrated over all incident directions. The bolometric, the average bolometric normal albedo is integrated as shown below, just over the wavelength, since the direction is set normally. Several authors, Dolphus and Bowell, derived the normal albedo from telescopic observations of the near side of the lunar surface. The measurements were made and averaged for 14 different regions over a wavelength from 0.327 microns to 1.05 microns. So the following relation was derived to fit the normal albedo to the observations. Since the observed waveband does not include the entire solar spectrum, the solar spectrum would go up to 3 microns. The normal wavelength dependent albedo is integrated against the truncated waveband to obtain the bolometric normal albedo shown below, and that's approximately the value that we use for albedo in the Disney is 0.12. This is recommended for orbital calculations involving a radiatively participating lunar surface, as described in the Disney section. It's interesting to know that I think we had a question on it a few minutes ago, is that the Disney also differentiates between Mare and Highland albedo, and this average kind of falls in between, just about in between the 2 extremes. For detailed thermal modeling of the lunar surface temperature, a solar incident angle absorbance obtained from the direct measurements of Apollo samples or correlations may be used, or on lunar surface temperature by several authors, including Kime, Williams, Vasaveda, Hain, or Feng may be used. I believe all of those authors used data from derived data from the LOR Lunar Reconnaissance Orbiter measurements. You can see that the solar absorptance is very high at near normal angles, but will decrease at very high incident angles down to much lower values. The directional, spectral, and total emittances of the Apollo samples have also been measured. The equatorial emittances have been derived from the channel 7 LR diviner brightness temperatures, which fairly represents the actual kinetic temperatures. The total emittance, infrared emittance, is shown as a function of temperature based upon the Apollo 11 and 12 lunar fine samples, and ranges between 0.92 and 0.98, with some variation according to density. And then the equatorial emittance from Vasaveda is shown below. The solid data line is smooth over 3 degrees of longitude for every 0.05 degrees, and so you end up with an emittance of approximating between close to 0.98, which is similar to the low temperature Apollo measurements. The recommended values in the Disney for remissivity are for the Highlands and the Mare mean are both 0.95 to 0.98, and in the South Pole we recommend using the Highland equatorial values. We don't have data available, and I was a little bit remiss. I should have put the absorptance, solar absorptance table in here, but there's a table in the Disney for solar absorptance for the Mare and Highlands in section 3.4.6, I believe. And then I think Lisa, are you ready to go ahead?
Can you all hear me?
Yes, I
Yes,
can hear you.
sir.
Okay, sounds great. Okay, so for the bulk properties of, or for regolith, we typically consider its properties as bulk properties when we use it in thermal models. The bulk density of regolith, if you look at a sample, it depends on grain type, size, density, its porosity, how much it's compressed, and if ice is present. And these parameters are based on where you are on the moon. And because of this, density can be thought of as dependent on depth and location. Here is a plot that shows bulk density versus depth at the Apollo 15th landing site. This is a plot from the Lunar Sourcebook. Near the surface, the density is much smaller, and then it gradually increases to near constant density as you get deeper. So for the creation of lunar surface models, you can use a global density versus depth curve that has been developed as part of a larger effort to determine global regolith properties that recreated nighttime temperatures that were measured by the LRO Diviner experiment. So you can go to the next slide. So this is the Hain 2017 global density relationship. It is an exponential relationship between density and the depth over a location-dependent scaling factor, which is that H factor you see in the equation. The H parameter, it accounts for the variation in local properties. So different H parameters were calculated for all the different sites between plus or minus 70 latitudes, and within that the typical range was between 0 and 0.1 meters. You can see on the plot on this page how the different H parameter impacts the depth versus density curve, and if you have a larger H parameter, the density is smaller near the surface, and you need to get deeper in order to have the density get greater. The average H parameter for plus or minus 60 latitude is 0.068. So none of these were calculated at the poles. There has been some recent work by Siegler and Fang that calculated the H parameter for a handful of polar sites, and they saw some values. They derived some values around 0.2 and 0.4. So ping me if you want the name of that paper. So you can go to the next slide. So this is a snippet of a Lunar Quick Map website page, and it shows where you can find the H parameter for any particular point within that plus or minus 70 degrees latitude. So if you're looking for it, you can just put a point on the page, and then you can look at the specific products available for that point and scroll down and find the Diviner H parameter, which is highlighted in red. Okay, you can go to the next page. So the bulk thermal conductivity of lunar regolith accounts for the conduction between the grains, the conduction through the individual grains, and then the radiation between the grains. And it depends on the material composition, the temperature, and density. The theory for the conduction and radiation and how it relates to the thermal conductivity of the properties is discussed in the guidebook, but I don't have it included here for time reasons. This is a plot that shows the thermal conductivity of different Apollo samples that have different densities and had different compositions. So you can see that there's a decent amount of variation, but they're all very low values. If you're creating a lunar surface model, instead of worrying about finding the right thermal conductivity versus temperature curve for a particular location, you can use one of the global models that have been developed. So you can go to the next slide. Okay, so here are two plots that show the thermal conductivities predicted by two good models for thermal conductivity that you could use if developing a lunar surface model. The Hayne 2017, which is what I've been referencing for, or what I referenced for density, is sufficient in most cases. It's less accurate for permanently shadowed regions where you get very cold because it doesn't capture the theory of the thermal conductivity approaching zero as the temperature approaches zero. So Martinez and Siegler in their 2021 paper include a proved analytical fit for low temperatures. So if you go to the next slide, it'll pop up an image that shows a comparison between Haynes curves and lab data for a lunar simulant. And this is a picture from Martinez and Siegler's 2021 paper. Okay, so that's it for thermal conductivity of that. Okay, the last thing I have for thermal conductivity is an extension for icy regolith. So I included this because if you're looking at an application where you might want to take a piece of lunar regolith and then extract water from it, Rice in 2018, his work gives a semi-empirical model for thermal conductivity of regolith samples that it counts for the presence of water vapor between the voids and ice between the voids. So here is a picture of the equations used for the extension of ice. It kind of uses a filling fraction to account for the presence of ice improving thermal conductivity. And the plot here shows the bulk thermal conductivity of a regolith sample that has ice originally and then water vapor between the grains. And if you're looking for properties of ice at really low temperatures, I recommend the IAPWS Python package that's linked right here. And I see a question that says, are the slides for the short course available online? They're going to be available online. Okay, you can go to the next slide. Okay, so specific heat. The specific heat theoretically depends on the molecular structure and the temperature, and the specific heat of many Apollo samples have been measured. The measurements have generally been taken between 80 Kelvin and 360 Kelvin. Here is a table that's taken from one of the old papers that presents specific heat versus temperatures measurements for Apollo samples. And lunar regolith specific heat versus temperature curves have been developed that are intended for use for thermal models of the lunar surface. So if you go to the next slide, I have a plot that shows several specific heat models. Again, Hayne 2017 has one that you can use. You can basically use all of Hayne's properties if you're creating a lunar surface model if you'd like. Woods-Robinson 2019 included an improvement for better properties if you're looking at that less than 100 Kelvin region. And because specific heat data of lunar regolith didn't exist at low temperatures, their curve included an analytical fit to Breccia rock that was taken at measurements from 3 to 4 Kelvin. However, Martinez and Siegler, their recent work determined that there was only a 2% difference in their results when they used the Hayne versus the Woods-Robinson model. So you probably don't need to use the Wood-Robinson model if you don't want to. Okay, you can go to the next slide. Okay, so lastly, I wanted to include some important parameters because these are useful for creating the models of the lunar surface. The first is these are thermal wave and skin depth. So thermal wave gives you the range in subsurface temperatures versus depth, and the skin depth is the depth where the dineural thermal wave decays to 1/E. Both of these parameters have been used to determine how deep you need to model your ground and what the subsurface discretization you want to use. The skin depth ranges from approximately 4 centimeters to 10 centimeters, and the annual thermal wave is deeper than the skin depth. There is a picture that is from the Lunar Sourcebook that shows the temperature swing versus depth that was taken from the Apollo 15 and the Apollo 17 in situ measurements. You can see that there's some variation between the two, but the main takeaway is when you're closer to the surface, you have a much larger temperature swing that's observed. And then as you get deeper, at some point you hit a point where the ground temperature is mostly constant over time. Okay, you can go to the next slide, which is the same slide, but a new picture that shows the difference, or it shows how the different H parameters can impact skin depth and the thermal wave. And this is a picture from Haynes' 2017 paper. Okay, so the last slide I have here is the ground heat flow, which Brian mentioned already. This just includes a little bit more of the theory. So the ground heat flow comes from the ground heat flow that's imposed on like the top about 2 meters of the regolith surface comes from radioisotope heating. So the radiation is actually emitting a heat flux onto the surface. And the heat flow has actually been measured at the Apollo 15 and 17 landing sites, and those values are included in this table. However, the folks who conducted that test also determined that because there's a higher amount of thorium, which is a radioactive material, in those landing sites, that's likely going to produce a higher heat flow than it would be globally, so then they calculated a global average. And since then, there's been subsequent work that has been used to determine the subsurface heat flow in a couple other locations. And that is all I have.
Thanks, Greg and Lisa.
Yep.
Okay, so now we'll jump into Brian. He'll be going over lunar orbits.
Okay, so this is orbits, but I'm really going to be talking about representing an NRHO in a thermal analysis. How would you do that? There's a couple of ways. But first, talk about orbits in general. The motion of a spacecraft is governed by an infinite network of attractions, right? Gravity is a long distance force, but you can't analyze that, especially in the solar system. But we're able to simplify things if the motion of a spacecraft is dominated by a single central body at a time. So that led to very useful Keplerian assumptions of two-body motion.
Brian, we can't see your screen yet.
Really? I keep sharing the screen and it doesn't let me do that. All right.
There you go.
Now.
There, we got you.
All right. So thank you for telling me that, Carlos. I appreciate it. I'm used to the little red border around the screen in team sharing, and you don't get that with WebEx. That's my cue usually. So here we go. We have back to the assumptions, and no forces are acting on the bodies except for the gravitational forces along the line of centers for those two bodies. But what about an orbit about a Lagrange point, right, where it's gravitational forces of two outside bodies, the Earth and Moon, are in balance, such as an NRHO. It's not a two-body problem, right? It's now under three. You can't. Tools that we have, thermal desktop and others, they don't have a three-body orbital capability. So do we have to use complex vector lists that we would get from, I typically get the vector list from our guidance, navigation, and control group. So here at Marshall, or at least in EV, that was EV40. That's the same group that holds the environments task, but they also have a GNC group, and so this is a vector list from them. Hey, I need to do a thermal analysis. Where's the vehicle at any given time? Since the NRHO is unstable, there's perturbations to the orbital parameters as the spacecraft orbits. They've got to be corrected, or the spacecraft will not maintain its orbit. They're small, but they need to be done. It's not a Keplerian orbit, so a vector list is the only way to represent the exact orbit and that's a keyword, exact, in Thermal Desktop. So here on the far right, I have a representation of the path of the spacecraft, I guess, as seen from a point on the Earth, or not a point on the Earth, but seen from the Earth center. So what this is it's the NRHO vector list about the moon, and I've corrected it for the sidereal or synodic period, or sidereal period, so it's for a single point or from the center of the Earth, and so you can see that orbit's just sort of wobbling. So we need to look at, well, if we're going to simplify this to a Keplerian or something we can use RadCAD for, or some other similar tool, we need to look at, well, how do we simplify that? Because typically we're limited to Keplerian orbital inputs. So let's look at an average periapsis or apoapsis and orbital period. So the period does change in the decimal places, but you get an average period of about 6.58 days. So that's just taking green to green or blue to blue points, and you can get the periapsis and apoapsis radius. Can we simplify it, right? This particular vector list had 52,000 positions. Actually never did shoot RadCAD for them. Not every position is needed. They are spaced evenly, but you could, they'd be more useful if they were concentrated closer to the moon. Ways to simplify it: you can sample the data, like say every thousandth point, or removing data point or vector points beyond a certain distance where the moon is relevant to a thermal analysis. So you just stop after you get so many planet diameters away from the moon. But another limitation is a vector list is an as-flown trajectory. It doesn't necessarily envelope hottest or coldest thermal mission relevant environments, right? Are you flying over the subsolar point? Are you staying over the terminator? What's the duration of a shadow period behind the moon, or something like that? So you've got those seasonal variations, off-pointing cases, because it's also telling you how the spacecraft is pointed, but maybe you want to aim another surface or a particularly vulnerable subsystem at a one environment or another. You can't really do that easily with a vector list. You've got to do a bunch of vector matrix transforms. But with a Keplerian orbit, you can easily do more simple rotations, and the orbital parameters can be tuned to envelope those environments. So how can we get or emulate this NRHO with a Keplerian? Several people came up with solutions. One, you just make a Keplerian with the same orbital averages if you're just doing one pass, and that's close enough. But what if you want to do multiple days, so something that's in orbit for a significant amount? So if you just put in the periapsis and apoapsis of altitude, that should just be both altitudes. The period between the vector list NRHO and the elliptical orbit are different. You can see where it start getting out of phase. So the orbital period in Thermal Desktop gives you about 7.5 days versus the 6.5 days for an NRHO. And the eccentricity is really close, but that the NRHO average E or approximate E, right? It's not really eccentricity, is like 902. So there's a little bit difference in that as well. So that changes the approach vectors that the satellite has when it gets close to the moon. But all this difference is just because the spacecraft isn't just orbiting the moon. It's actually orbiting that Lagrange point in the Earth-Moon system. So for Keplerian, if we assume that it's described by a conic section, and even maybe the NRHO, if we assume that we can approximate it with a conic section. So how do we change that orbital period? So we can do a multi-orbit analysis and get that periodic thermal input from the moon as we do those close approaches. So we can change either the gravitational mass or the semi-major axis. I've got the Keplerian, period equation over there on the right, and that's really the only two inputs you have. Changing the moon's mass causes a couple problems, such as the spacecraft velocity at the periapsis and also the time spent near the moon. So I'm not as big a fan of that method as just going with the semi-major axis change. So here, I changed the apoapsis, or the maximum altitude. What that does is it keeps the distance and true anomaly versus time very close to the NRHO vector list while matching the orbital period. So here you have a adjusted apoapsis, and you can see the path by the moon on the far left-hand image to scale is very, very close. Here, the blue line represents the thermal desktop Keplerian, whereas the orange is the vector list. Then you have the comparison of over time of the spacecraft distance to the surface of the moon in planet radii, and they're very, very close. And I've even plotted the error band. So you're right around, you get up to about 6 planet radii, you're about 2% difference in distance. So again, this method gets you a very close approximation of an NRHO pass around the moon using the Keplerian tools available in our thermal analysis toolkit. And the only thing that changes really is the distance our spacecraft flies when it's far away from the planet. So instead of being 42 moon radii away, we're about 38. And again, we are well outside the influence of the planet thermally on our spacecraft at that point. The way to do that is just really simple. You just type in the minimum altitude that you want, so closest approach where it's thermally relevant, and you give it the NRHO period, and it will calculate the maximum altitude for you, which you can see is different by about 6,000 kilometers, give or take. It's kind of a really quick approximation of it. And just to show that it does kind of give you the right environments, here's a comparison of incident heat for solar, albedo, and planet shine sources for the vector list that's in yellow, and then Keplerian orbits that are tuned to fly over the terminator or the subsolar point. So yellow, orange, and green are my curves here. The Keplerian times were offset for comparison purposes. So we're talking things are shifted in time, just so you can sort of see the traces side by side versus them overlaying each other or being on vastly different timescales. So you can see where they compare very good. So solar, it's the same incident solar flux. You have shadowing regions for about the same time. Here for albedo, for a over the flight over the terminator, you've got very similar incident heat. And then over the subsolar point, you can, it was close to subsolar, wasn't quite subsolar for the vector list. So the Keplerian orbit is going to be a little warmer. And the same thing for planet shine for the same reasons. Additional control using the Keplerian approximation allows for enveloping conditions. Here I got a little, about 69 or 69.5 minutes of eclipse time versus that 73-minute time that I showed in the previous set of slides. Spacecraft pointing can be tuned without needing additional vector list or modification of the existing input that you've gotten. Another very nice feature, at least within TD, is using Keplerian gives you better graphic visualization of, or easier for me to understand at least, of where your spacecraft is in relationship to your solar vector, your shadow cone. This is colored by IR planet shine, so I can tell that that's correct, right? At least those environments are lined up, and that's not necessarily available when you're showing it as a vector representation. If somebody online is able to do that while you've got a vector representation, please let me know, because that would be nice. But this is just better for visualization of what's going on. Also, when you're pitching out results, it's kind of more descriptive to show sort of what the spacecraft environment is the spacecraft is seeing during the analysis. I think this is the last slide. So for LLO and well, other considerations, right? The periapsis is high enough with a wide view of the surface below it as the spacecraft approaches the moon. We've kind of come to the mean albedo and emissivity values are probably sufficient because you've got such a wide view of the moon. However, you can still bias it using this table. But as the altitude decreases, so does the field of view of the orbiting spacecraft to the moon. And so it's more likely that you will see only an area that is defined by one of these enveloping cases. So if you're doing an LLO or even an ascent-descent trajectory, I really recommend using these albedo or OLR biased values in the analysis. Speaking of ascent descent and the time constraints of this short course, I would like to point you guys to a method developed Alex Sherzan and others here at Marshall in the ES group. They presented this at TFAWS 2019 to incorporate ascent and descent vector lists into a planetary lat, long, and altitude orbit with some transforms to get that 6 DOF trajectory into the, I think, 3 DOF rotation options within that orbit. And here I've listed the PowerPoint slides from TFAWS. I linked to it, and also the paper that was presented. It's a very in-depth method, and here is where you may even go and use those mapped albedo and emissivity values that I had in an earlier presentation as you get really close to the surface. I think that's it, Carlos.
Thanks, Brian. All right, so actually finished quicker than I thought we would. We have a total of about 15 minutes left before we break for lunch. Jedediah, I have a quick question. If folks do have questions, they have to put it in the chat, or do you have to unmute them?
Chat is preferred.
Chat is preferred, okay. Yeah, so we have 15 minutes, folks. So if you have any questions, feel free to ask.
Carlos, another option would be to go ahead and move my next slides to now.
Oh, I think we can. Yeah, we got 15 minutes.
I mean, we may go over 5 minutes or so into lunch, but.
Okay. Just start it off, and then we'll start off with the video later on.
Yeah, I mean, that way I can become a spectator for the second half.
All right. All right, yeah. Go ahead and start.
All right, so, okay, I think I'm actually sharing this time, Carlos. Can you make sure of that?
No, not yet.
Not yet? Okay, again, O for whatever I am.
There we go.
All right, so I developed this slide deck kind of as a tutorial for environment calculation and setting up heat rates and RADK calculations in Thermal Desktop. So you'll have to forgive some of the animations, but this was during COVID timeframe, and my kids were helping me do this, so we really exhausted the animation possibilities within PowerPoint. So again, apologies in advance. So in Thermal Desktop, there's 2 types of radiation tasks when you're setting up analytical environments, or that are relevant for this, are the RADKs, right? Thermal exchange between your model surfaces and heat rejection to space. Model it as energy exchange, right? Q space is equal to, the view factor emissivity of the whole K value, and then the temperature differences to the 4th. The other one is heat rates, and these are directional and diffuse heat loads applied to the model. They're typically defined using orbits in the orbit manager, and they're modeled as incident fluxes. So this is incoming heat loads, and it's a sum of everything solar, albedo, planet shine, so on. And they're calculated and applied. These 2, RADKs and heat rates, are calculated and applied independently, but they result in the following equation, where you have incident heat loads, and then you have the radiation exchange to space. So the view factors and stuff are sort of overlaying each other, if you would. But the energy is balanced. So again, here come the animation. So let's look at the rad case first, right? So you have a space node and it sets the radiation sink temperature of your model. And when it's applied to the spacecraft, there's the energy exchange. When I'm talking to people, I like to, so K is a gray body form factor to space for a node. So that includes the emissivity of your vehicle and assuming space is a black body. But I like to have people think of the radiation to space as two components, right? It's the incident in from the space temperature, 2.73 K, or whatever your background is, right? Whether you're TVAC or sitting in a office, that's your sink temperature. And then the outgoing radiation from your spacecraft or model element to that sink temperature. So you can divide it out that way. Looking at the heat rates, again, we have our spacecraft. So for terrestrial lat-long orbit, one nice feature that came about when I was first starting out here at Marshall, instead of having to model an entire huge ground plane, you now have an idealized planet that's below the horizon. And then you have a sky that's above the horizon. You have your solar, and so those components are, you have your direct solar, so that's straight from the sun onto the vehicle. Albedo, solar that's bouncing off the surface, and diffuse solar is, on a cloudy day, right? It's what's coming in from the atmosphere diffusely onto your spacecraft. There's also a component, diffuse sky albedo. So that's solar that's hit the ground, now has gone out to your atmosphere, and is now coming back in that same wavelength is what's important onto the spacecraft. And then as far as IR components are concerned, you have planet shine, which is below the horizon, and a diffuse sky IR, which is above the horizon. So this looks like what you would see for an atmospheric terrestrial Mars type of analysis, all of these different components. So what do you do when you're setting them up with an atmosphere or without, right? Combining those two heat rate calculations, rad K and the heat rate, gives you a term, the Q net on your vehicle surfaces is the heat rate plus the rad KQ. They're separate calculations. The rad K term doesn't really see the idealized planet surface. So, you have a modeled surface and maybe right underneath the footprint of your spacecraft, but any ray that goes in a downward trajectory that misses that does see space. So considering the IR wavelengths, right? Sky IR, the red arrows represent above the horizon, and ground IR is below the horizon in green, and also orange if you were to miss. They represent all the incident IR that's hitting your vehicle. So if you have something that's sitting on the surface of the planet, your sky temperature becomes the above the horizon sink, and so the T space needs to be 0. But now what if you're on the moon? If you're on the moon, you can still set T space to 0, and you can set the diffuse sky IR to be 2.73. And what that will do is it will limit the space influence to only above the horizon. So you're kind of working that system out a little bit differently. You're still setting space to 0. And what you've done is you've zeroed out this term because now T space is 0. I'm pulling this from the CD manual. It may be confusing to include a diffuse sky IR term in the heat rate, as there's no atmosphere, but space should only be visible above the horizon. Also, when you're on the moon, you have no diffuse solar and diffuse sky albedo. Those you set to 0. I think diffuse sky albedo you don't set to 0, but it is set to 0 when you set diffuse solar to 0. So setting the space node to the background temperature of space does create a flux from space above and below the horizon, regardless of your idealized planet surface presence. But you can model a large ground plane to block enough of the space flux below the horizon to be accurate. So if you do keep space nodes set to 273, a large model ground plane is required, especially when we're talking about polar regions where we're very cold, and that can have some effect. And then you can uncheck diffuse sky if you do set that to 273. So now the other part of this is sizing that ground plane. So in the first set of slides, I said, hey, the ground on the surface of the moon is participatory. You need to have that modeled in your analysis, not just the idealized plane, but what will be affected by the shadow of your vehicle on the surface. So in the guidebook, we kind of break the ground plane into two different sizes. One is a ground plane that's large enough to capture the vehicle's effect on the surface. So that shadows, where you'll start having cooler regions, where you've shaded the surface from the sun, or if you're talking polar analysis, even warmer regions where your vehicle is radiating downward to the surface and keeping it warmer than it would be if it was otherwise not in proximity to your vehicle. So thermal desktop, right? Thermal analysis tools can provide an idealized ground plane, but it's more of a boundary condition. But that can model the effect of the ground onto the vehicle. So I don't know if I got far enough here, but large enough to capture the vehicle's effect on the surface, and then the larger version is to capture the surface's effect on the vehicle. So the idealized ground plane does sort of substitute that bottom size category. It allows for much smaller model ground plane, right? You only have to capture the vehicle's effect on the surface, and it's less computationally demanding. I know back in the Constellation era, we had some models where we were modeling the entirety ground plane to get close to a 50% view factor on the vehicle, and you end up with very large conductors between those nodes and nodes on your vehicle. And it was and shooting the RAD-Ks and running those SINDA models started taxing the computational resources available at the time. I'm going to these charts are in section 9.3 of the guidebook. I'm going to focus just on this representation. There's several other representations, such as cylinders above the surface or spheres. Depending upon what you're modeling, whether it's a very tall object like a radio tower on the surface, or maybe you have just for argument's sake, like a water tower, right? Something on a very thin stalk with a large, maybe it's an inflated asset or some sort of something that's high suspended up off the ground, and you want to talk about that. There's a few other correlations that work better for that. For something that's either a short, squat, or even a aspect ratio very tall and skinny that's very close to the ground, or not a whole lot of gap between it and the ground, these two are very good approximations. These were put together by a visiting professor out of University of Alabama for the document. And the one on the left is how big does the ground plane need to be to capture the vehicle's effect on the surface. So as the ground plane gets larger, you follow these curves down until you get toward the ground plane or the view factor of the ground plane to the vehicle, right? Or the ground plane's view of the vehicle, that's probably the easier way to say it, is about 5%. And that's what this curve fit equation represents. There's another equation listed in the document that allows you to compute the entirety of these curves down to the percent error that you prefer to use. But for the sake of this presentation, we'll just use the 5%. This one on the right is, okay, how big does the ground plane need to be to capture the surface's effect on the vehicle? So here, you need to make a ground plane that's big enough that it is 50% of the view factor, as opposed to trying to get to 0, right, where the spacecraft is, or the ground plane is so big that the spacecraft no longer has an effect on it. Here, you're trying to get the ground plane big enough that it is 50% of the view factor of the spacecraft. And here's the curve fit to get within, I guess that's 5% error, so 47.5% of the view factor. Again, the equations for the entire line are provided in the guidebook, so you can get as close to the correct answer as you like. The difference between those two, right? So for a aspect ratio 5, so for something that is 5 times as tall as it is radius wide, the ground radius to capture the vehicle's effect on the surface needs to be about 61 meters. So that's a small ground plane. If you are not using an idealized ground plane in your model to capture the surface's effect on the vehicle, you've got to be about 450 meters. So that's where we start talking about that computationally difficult ground plane that you're modeling. It ends up being a very large surface. And so if you can use the idealized planetary surface, that allows you to use the smaller one. Some analyses and software tools may not be able to provide that idealized surface, so you would need to use the much larger ground plane. There's also some analyses within Thermal Desktop, some of the polar ones where you have the sun partially occluded by the horizon, that may actually require you to use a larger ground radius versus the smaller one, just due to the orbital, the way the heat rates are calculated between the different orbit options. So here's one of them: solar occultation. Cases with low solar incidence angles, planetary orbits may not be the best choice. Here, vectorless orbits, something like Greg can talk about, which you can also take them from a planetary orbit file. So you build your location in a planetary orbit, and from the HRA file, you can get the vector list and then throw it into a vector list orbit. They can allow for partial solar illumination, so the sun's only so far above the horizon. But the problem with that is, or not the problem, a small inconvenience with that solution is that SkyIR is not an option in a vectorless orbit. So you would either need to use a much larger ground plane or understand the effect of the thing I talked about earlier, of the usually small effect that a space node flux is having on your model. Instead of are you setting it to 273 or are you setting it to 0 to account for the above-below horizon effect? So that you just have to keep in mind that since you don't have the option to use a diffuse SkyIR to mimic the above horizon sky or space and exclude below horizon space, you have to take that account into your model. So here now how do you set the ground plane temperature? So if you're using an idealized planetary surface, right, you can use, for your modeled ground plane, it's going to participate in the analysis. So it will react, however you have it set up, with the environments and the interaction with the spacecraft that you have in your model. So the solar's going to hit it. You're going to have reflected solar and albedo going on with the spacecraft. So if you model the small ground plane, it will react appropriately depending upon how you built it. You can include capacitance and subsurface conductance and heat flows and all those things that you need, or you can use an arithmetic ground plane, which is more appropriate for equatorial or hot or more equatorial latitudes, but it does give a really good first order approximation. But now for the idealized ground plane, how do you set the temperature? When you do a lat-long planetary IR, that is fixed in space and time. It's a one-time point. So really you need to have a time-dependent ground plane temperature. So you can determine that surface temperature by solving that equation that we had in the first set of charts that I presented, the cosines of your planetary lat-long versus where the subsolar point is and all the other, or run the case with just only your ground plane. I added a heat load to correct for the unilluminated side temperature of about 5 watts, and I ran it steady state at each time in orbit position. And then you take the resulting temperature of your modeled ground plane at your location lat long, and you input that into your orbit as the idealized planetary surface. And then you can run your model with your small modeled ground plane and the idealized ground plane with your model in it and participating with the surface. But to get the idealized ground plane temperature, I recommend running a simple ground plane first to calculate it for your particular orbit timeline and your location, and then inputting that into another run. And so what that looks like is it sets the whole planet to a single temperature, but it's valid for your limited view, for the limited view of the terrain for a landed asset. And I combine it with the model ground plane any method, like I talked about, you can include the capacitance or conductance to account for the vehicle effect on the ground. This method also works for vector orbits. So here you use a ground IR versus time. You can input your table. You can use the temperature of your ground plane as the input. And this is sort of that profile. And this is what it looks like over time. You're in shade, you're at 100 Kelvin, because that's what I set it to in my calculations. You can use 120 or 80, depending upon how you're biasing the calculation. Then as you cross the terminator, you start warming up until you get the subsolar, and then that over time, as your model location rotates through the subsolar point and around, it cools off again to represent the temperature of the surface at your current location relative to the subsolar point.
All right, so we're back. All right, I just want to make sure everybody can see my screen. And so what we're going to show now is just a simple example on how to model a large lunar ground plane and a small lunar ground plane. It's about a 24-minute video.
Hello everyone. I'm going to demonstrate how to create a lunar surface model on Thermal Desktop with some tips and tricks. I want to point out that this is just a simple example based on the problem statement given. This is not a one-size-fits-all model, and it's highly recommended to make adjustments based on the complexity of your problem statement and the specific lunar environments you're trying to capture. Okay, so let's begin. So here's my problem statement. A spacecraft is scheduled to land on the moon for a demonstration mission. It will land during the new moon when the northern latitudes are in winter at a 1.54 inclination towards Earth. The landing site is 85 south, 53 east, and it's considered a flat surface. It will stay stationary in this location for a quarter of the lunar day before it returns to orbit. Create a lunar surface model which captures shadowing and the environment of the moon. All right, so let's see what we're going to cover. We're going to learn how to calculate the minimum radius for a large lunar ground plane. We're going to understand the orientation of the moon. And we're also going to set up a terrestrial orbit in Thermal Desktop. Okay, so for this example, we will build a large lunar ground plane. So let's calculate the minimum radius based on the dimensions of the spacecraft. The equations recommended is for a cylinder to ground plane equation where it is assumed that the cylinder is laying on the ground. And you can find this in the L tag. So right now, the spacecraft is 70 meters high with a diameter of 14 meters. You can calculate your aspect ratio with these dimensions. Then here's the equation. So right now, the minimum radius we have is 448.65 meters. So let's go ahead and see how that looks in Thermal Desktop. So here's my spacecraft. I already created symbols for this example. So I set it up here. So here's my large disk R, 448.65. Now let's turn on that disk, see how that looks like. Here you go. It's pretty large. One quick note. For improved accuracy, it is highly recommended to run a mesh convergence of the lunar ground plane. The mesh convergence determines how many nodes are required in the model to ensure the results of the analysis is not affected. The system response of the lander will converge to a repeatable solution after a certain amount of nodes and rays used in the model. So make sure your node count is not too coarse, which might give you the wrong results, and make sure your node count is not too high, which would increase your runtime and create an inefficiency by having unnecessary amount of nodes. So now let's see how the moon is oriented. The problem states that it's a new moon with the northern latitudes in winter. During a new moon, the far side of the moon is completely illuminated since the near side of the moon is facing Earth due to it being tidally locked. During the lunar winter solstice, the moon is tilted -1.54 towards Earth. In addition, the prime meridian is located on the near side of the moon from north to south, shown below. Now we could orient the moon. So to show you a little bit more, I actually have it back here. So this is not to scale, this is just to illustrate where we're at. So here's the sun, here's Earth, here's the ecliptic plane. Here's the orbit of the moon. And again, a new moon is when the moon is in between Earth and the sun. And this angle right here is the tilt of the moon. I just have it exaggerated so you could see it. But this picture right here is the same one that I have here on this PowerPoint. Here's the -540 degrees. Here's the sun, ecliptic plane, Earth. This is a side view. And keep in mind, the near side of the moon is the side that's always facing us. So the prime meridian starts from north to south, just like you look at it when you face up in the sky. So this is the orientation that we want if we see it from the top. Here's the Earth, we're viewing the moon. Here's the prime meridian, and the sun vector is coming from this direction. So let's go ahead and set that up. Thermal desktop. All right, so you would add. I'm just going to show you which one you would have to pick. Let's just call this test. You would select the planetary latitude, longitude, altitude. Once you select that, this is your terrestrial orbit that you would have to set up. I already have one created, so I'll just cancel out of this one. There's a large surface. Display orbit. Okay. So let's go ahead and turn this off, and I'll talk about that later. Let's turn off the vehicle, the model. Okay, here we go. And let's talk about these angles right here. The right ascension of the sun and the right ascension of the prime meridian. So by default, let's turn this. If you look at it from the top, here's your XYZ axis. If you look at it from the top, you can't see it, but the moon is tilted towards the Y direction. So here's your sun vector. It's tilted towards the Y direction. I have it right here. Here's the top view. Here's the thermal desktop default. Tilted toward the Y direction. Your prime meridian is right there in the X facing the sun. So what we want to do is that we want to rotate the sun 270 degrees. And we mentioned this in the L tag. So there's more detail on that in that document. If you want to look at it. So we will rotate this 270 degrees. Once we set the sun, now we got to move the prime meridian, because remember, like I mentioned before, is the sun is facing the back, the far side of the moon, the prime meridian's facing Earth. So here, now we already have the sun, the far side of the moon. Now we got to, well, we got to move the prime meridian so we could be at the far side of the moon. So the sun could be facing the far side of the moon. So remember, it's 270 for the right ascension of the sun, 90 degrees for the prime meridian. Let's go back here. Just edit the, here we go. Here's 270. Here's 90. Done. Okay, here we go. Here we go. So now we're set up correctly. All right, so now let me show you how to set up your location on the surface. So the easiest way to do that is if you go to your planetary data, here's your mean solar day, which is also the synodic period. So what I did is I just get the time here. I put it in Excel. So here's my mean solar day, divided it by 12, because again, for this example, I'm just going to do 12 locations. Then I just did the math for to see what it looks like for hours and days, just double check it, and it's right. Remember, mean solar day is 29.5 days. And then from there, you just copy this column, you set up your lat longs. This is your altitude. Again, since we're on the surface of the moon, we don't need to put an altitude unless you're doing that type of analysis. Also, you could rotate the spacecraft around the z-axis. For our scenario, it's not rotating, it's just going to stay fixed. And also, I wanted to point out that this angle right here corresponds to the position that Thermal Desktop is gathering data. So I want to know, quick note, you could refine this more. It's based on what exactly you're trying to get out. If you're trying to get more detail in some temperatures on your model for a specific time during your orbit. So that's just a tip right there. All right, so I just grab this right here, copy it, you go to your lat long, paste it, and you're set. Okay, so now let's see where our spacecraft is located. So let's go ahead and turn it back on. I modified the scale factor and the translation factor just so we could see it a little bit more. So there you go. We're in the southern part of the moon, the South Pole. Okay, so let's see how we set up our optical properties and our thermophysical properties. So all you would have to do is set up your optical properties for lunar regolith, which you could find in Disney. I already have some set up, which is just some mean values that I found. So you could see here, for this disk right here, you only have the top on, the bottom's off. You're only going to shoot rays from the top. Here, this is the property for my lunar regolith. And for my thermophysical properties, I have these values right here. And I just left the thickness as is by the default value. Okay, now let's look at how we set up our case sets. Here's my case for the large surface. For your radiation tasks, you would need to add heat rates and rad case. So for your heat rates, you select the orbit that we just created, the terrestrial orbit for the lunar large surface. Our heat rates are only solar. Make sure these are unchecked. For your rad case, you could just leave them as is. Okay, I already have some results for this because I already ran the model. Oh, before I start, I want to point out that I did put in some optical properties for the spacecraft. For the surface, I put on this Z93 white paint, beginning of life. And for thruster, I put in just black paint. So you're going to notice with the results that the nozzle was way hotter than the rest of the spacecraft. All right, so here's our solution. This is for position 0. Let's look at some other time. Select this one. Or we could skip through time just to see how it looks like. But yeah, see, you can see how the shadow's starting to form. Here's the sun. And you can see it rotate. Let's zoom in. There you go. There are your shadows being formed. Now, another thing I want to point out when you're using a terrestrial orbit here is that the terrestrial orbit fixes the season, meaning that it stays tilted in the direction that we set it. So it doesn't take into account any seasons at all. For the most part, if you're close to the equator or even the location that we're in, and especially with the assumption that it's a flat surface, it's okay. It's okay to use a terrestrial orbit. However, when you start going to really high, let's see, let's go to Orbit Manager. Display orbit. Yeah. Once you start getting a little bit really, really low latitudes, really, really high latitudes, especially if you're in a crater or if you have, these giant boulders or mountains, obstructing the view of the sun, it's going to make a difference. So it's highly recommended to use a vector list in this case. And a vector list, when you go to create an orbit, go to add, and you select this one. Now this would be explaining another video, but I just wanted to point that out. It's a quick note on if you want to take into account the seasons, we recommend a vector list. All right, so that's how you make a large lunar surface model on Thermal Desktop. So now I'm going to show you another method of modeling the lunar surface using a smaller ground plane and the idealized ground plane provided in the Orbit Manager. This is a great option if you're trying to limit the number of nodes in your model and want something that's less computationally demanding, especially if you are running parametric studies or optimizations in your lander model. Okay, so let's start by calculating the smaller ground plane radius. So just like we did before, we went ahead and used the same dimensions for the diameter and the height of the lander. And we're going to use the ground plane to cylinder equation, which is located in the L tag. And using this equation, we get a radius of about, if we round up, 61 meters. So let's go ahead and see how that looks like in our model. So here's our large ground disk. Now let's turn on the node so I could show you in comparison how small the ground plane looks like. And in comparison, so here's my small lunar ground plane and here's my large one. So you can notice immediately just the amount of nodal reduction you have just by using this method. All right, so let's turn these nodes off and set this back to its original value like I had it. And now you can see the small disk. So just remember, with this option, the assumption is that the effect of the ground to the lander are significant up to 60 meters. So it's from the center to the radius, which is 60 meters. Everything beyond 60 meters could be represented and replicated using the ground temperature with the idealized ground plane, since the effects are either very small or nothing at all. Okay, so now let's create the idealized ground plane. Let's go to our Orbit Manager. I essentially just copied the lunar large surface orbit and just renamed it lunar small surface. So my lat longs are the same, my right ascension of the sun and the prime meridian is the same. So there are two things you need to change in your Orbit Manager. You go to your diffuse sky IR and you set it to 2.73K. Then in your ground IR, you can notice that I have use ground IR versus time checked already. And here, what this is this is the temperature that we're assuming that's beyond the 60 meters that the idealized ground plane is going to be. And I want to show you how to get this temperature, because this is a temperature as a function of time, which is for one whole period, which one single day of the moon. So let's get that first, and then we'll close this out. All right, so all we really do to get that temperature is I created a large surface only case set, and where the only thing I have on The only thing that I'm running is the large lunar surface. And I'm just running it. It's a steady state. I'm running it for a full lunar day. And let's look at those results. Let me turn this on so we could see it. All right, so here's the large disk. Let's look at those results. Surface only, set current. And you can see here, see how the lander's grayed out because it's not in the analysis. It's just a disk. Here's the plot. This is the plot of this is the temperature plot of all the nodes on that disk. And they're all the same because there's nothing obstructing direct solar to cause a shadow for some other parts of the surface to be either warmer or colder temperature. So that's why they're all the same temperatures. So all I did is I just took this solution, the results. All right, so here is my results. It's the same plot that the same plot that you see in the XYZ plot. I essentially just grab all of this right here, copy, go back to the lunar small surface, ground IR, open this up, paste it, and you're ready to go. So that's how you set up your idealized ground plane in the Orbit Manager. Now let's go set up your KSET. So here I have a small surface case. All you would have to do is on your rad case, your space node, set it to 0. For your heat rates, make sure you have solar, planet shine, albedo, and diffuse sky IR checked in your control. Solar, planet shine, albedo, diffuse sky. Okay. Now let's run this. I already ran this model. So what we're going to do is we are going to compare the large lunar surface results versus the small lunar surface results. See how far off we are. So what I'm going to do is I'm going to compare these two nodes right here, one of the purple ones and one of the gray ones. And let's go ahead and select this middle surface that's in between the cylinder right here of the lander. So I already have these results post-processed. So if you can notice, the large disk and the small disk, that specific node, they're essentially on top of each other. There's no significant difference. Now, when you compare the lander, that node on the cylinder itself, here's the lander with the small disk is the dotted line. And the solid orange line is the lander with the large disk. And you can see that it pretty much matches it. There is some differences in between right here, but then as you continue going, it starts matching up again. So this is a method that we highly recommend if you want to reduce your node count. You can notice here that the lander with the small disk and the lander with the large disk, when you plot the temperatures of the side of the cylinder, you pretty much get the same results. And if you're running models and where you have intricate, detailed compartments inside your lander and you're trying to get quick results because it's part of your design process, this is something that we highly recommend for you to do. There are its pros and its cons, but for the most part, for your first step, this is something that works out pretty good.
I see a question out here that says, for ground surface, does it make sense to use a boundary node at a depth below the surface and let the surface temperature be calculated accordingly? Do you want to go ahead and respond to that, Lisa?
I can do that. So The subsurface temperature at the deepest node varies based on location. So if you just set it to a boundary node, you wouldn't be correct for every location. So you would need to determine that in advance. For example, at Apollo 17's landing site, the subsurface temperature approaches about 255 Kelvin. If you do the theoretical calculation for 85 north latitude, then your subsurface temperature gets about 160 Kelvin. And then for permanently shadowed craters on the South Pole, the subsurface temperatures can approach 35 to 50 Kelvin around that 2 meters depth.
All right, thanks, Lisa. Okay, and there's another question right here. If a rover covers an illuminated portion of the lunar surface, I'm thinking Viper on the South Pole, will the lunar surface temperature start to drop considerably over time, such that it should be modeled? You want to go ahead and answer that, Brian?
Yeah, I can answer that. So yeah, we haven't covered transit shadows here in these charts. Looking at, I presented a chart earlier where we looked at the time of thermal response for the surface during, say, a lunar eclipse, right, where something is suddenly covered up and doesn't have a shadow. And it did not take very long at all in the term of a lunar day for that surface to cool off drastically. However, how long would that rover cast a shadow over a given area of surface? And also, it's a polar mission, so the temperature change wouldn't be as great as those measurements that I showed that were taken closer to the equator. In fact, because it's polar, there may be cases where the rover's crossing might increase the shadowed surface temperature if the rover is warmer than, or radiating more energy to the surface than what it would receive if it was not shadowed. One approach that has been taken for that exact question is to bound the analysis, right? Where for a hot case, you leave the surface at its warmest, whether that means it's illuminated or it's warmed by the rover. You don't, as a boundary condition, you don't bother with the participatory surface at that point for a hot case, and then also at its coolest for a cold case. So in that case, you're enveloping the analysis instead of trying to take into account a very transient surface temperature change.
Thanks, Brian. Okay, so now
there's also a third one, Carlos, that came to me. I also put it in our offline chat. It's from Kimberly. Regarding sizing of the ground plane, are there recommendations for the mesh density of the ground plane? And so that one has a very generic answer, which is you increase the mesh density until the model results stop changing. But that's very time consuming. At extremes, a single node will not capture shadow effects. And you can actually transport energy from illuminated lunar surface into the shadowed region under the vehicle if your mesh is too coarse. Too dense a mesh, right? You got a bunch of nodes that have the same effective view factors to the environment and your surface surface asset nodes, and then they have the same temperature profile, and that's a huge computational cost. In my example, and Carlos, is like with a simple ground disk close to the vehicle, the node density ought to be able to capture the shadow outlines as the solar altitude and azimuth changes. Angularly, what I would suggest is, the node count on your vehicle is usually a function of the number of thermal sides of the surface asset or your rover or whatever, and the number of orbital time positions in a planetary case are defined, or you have to make that judgment as to how many you need to capture the environmental effects on the surface vehicle. The ground plane can then have that same count angularly, or some multiple of that to capture the shadow effect. Radially, so going from the surface asset and out to the horizon, the nodes definitely can be sparser the further you are from the asset, the surface asset. General guidance that I give people is try to build the ground plane so that no single ground node has more than a 1 or 2% view factor, is 1 or 2% of the view factor of a single vehicle node. There's obvious exceptions like landing leg or pads or wheels for rovers, where you're going to have a larger view factor because you're that close to the ground, just in extreme proximity. But if you can minimize the effect that any single ground node has on your vehicle, then you've probably got it meshed to a reasonable density.
Well, good afternoon. This is a short briefing on using a vector list. The vector lists are derived from the JPL Horizons application, the ephemeris, and converted into a thermal desktop orbital vector list. And this is just describes the process on how to do that. The default application, you see the link there below for the Horizon system. When you bring it up, it'll default to a number of options for the 5 main settings. I'm not sure if these are the actual same defaults you'll get if you bring up the application. The browser will actually save your settings from a previous session as well. So I think these may be the actual defaults, though. The application allows placement of an observer anywhere on or above the surface of the moon or other objects in the solar system to track a target body, such as the sun or even the Earth via the parameters. The elevation angle and azimuth are convenient for conversion into a vector list that commonly used by thermal analysis applications like Thermal Desktop. So this is what as I said before, this is the initial pane that you're greeted with. And so each setting in the Horizons application may be altered through the edit button. If you need to set the ephemeris type into observer table, if it isn't already. If it is already, you can just leave it alone. And then you'll want to, for our application, for a lunar surface orbit, effective orbit, we want to change the target body to the sun. So we choose edit and then select from a list of major bodies in the pull down menu, and we can select the sun from the options provided. We could also, as I indicated, target planets or other celestial bodies as well. For the observer location, you want to choose specify coordinates from the pull down menu. You can change the coordinate body to the moon by selecting from a pull down list. If you go through the pull down list, you'll notice that there are many options in there for all sorts of moons in the solar system. And you'll just advise you that you'll have to scroll down a little bit to find our moon. You'll want to enter the desired longitude, latitude, and altitude into the display dialog. For the southern hemisphere, you would use a negative latitude and then positive latitude for the northern hemisphere. And the body ID for the moon is 301 in the Horizons vernacular. Note that the altitude is specified with respect to the reference ellipsoid surface for the moon. And typically, I think the results I'm going to show here coming up are for 0 meter altitude, but you can place an object above the surface if you want to, as high as you want to, if you wanted to simulate what the solar vector would be on the top of a peak or side of a mountain or whatever. You also want to enter a time specification with the begin and end dates for the ephemeris, and a lot of times I'll just run it out over a year, so I can see the total variation, and by doing so, I don't have to worry that much about the start, the longitude. If I'm not really that worried about the longitude, and I can look at the variation over a calendar year, and you'll also enter step size, which typically, 1 day might be sufficient. So you would end up with 365 or so data points. You can edit the table settings to display whatever options you desire. There are nearly 50 options and all sorts of things you can pick. So there's probably a lot of untapped potential with this application. As far as I'm concerned, I've only used a small part of it. Typically, for what we're doing in this case, is I would select number 4 to output the apparent azimuth and elevation. So that'll give you the elevation angle to the sun and the azimuth relative to the local coordinate system, which I'll show in just a minute. Sometimes you might also pick the target angular diameter. That would be for our sun. That would be the angular diameter of the sun, which can be useful for some calculations. But then there are many other options available, as I indicated. Once you run it, this is what the final table would look like, or the final input pane would look like with the settings. Observer table, target body is the sun, the observer location. This is for a negative 89.5 or an 89.5 degrees south 0 kilometer moon location. And then we have the time specification over approximately a year, well, actually 13 months, with step size of 1 day. And then the table settings are per what I prescribed previously. If you look at you'll get a text output that'll be provided as shown below. It'll give you the date, and then you'll have the azimuth angle, the sun elevation, and then the angular diameter of the sun in arc seconds, which is going to be on the order of a half a degree typically. As far as to convert the ephemeris output, the columns are as I indicated. If there's a star symbol, that would indicate that the location or the observer is in daylight, or the solar upper limb is on or above the apparent horizon. Absence of the symbol indicates nighttime or the sun is set. That we didn't see a star on the little snippet I showed below, and you notice that the elevation angles were negative, so the sun had set below the horizon. The solar azimuth and elevation angles may be used to derive a unit vector for the orbit description within Thermal Desktop. If the z-axis is the local vertical, with the x-axis would be pointing to the lunar North Pole, a local coordinate system may be defined as shown. So if you take the cross product of x and z, then that'll determine y. The elevation angle is denoted as theta sub a, and the azimuth angle is denoted as alpha in this definition. The vector to the sun, a unit vector to the sun, can be defined with the trigonometric relation below. You can calculate that as the product of the cosine and sine of alpha and theta, as shown below, and get a vector definition for unit vector for I, j, and k. If you want to put this into an application like Thermal Desktop, you can input the vector directly as the sun vector. That I typically take the azimuth and elevation angle and input that into an Excel spreadsheet to generate the orbital or the sun vector. And I think Ruth Adamson from Langley has an example of this on the NEN website on the or a spreadsheet that you could use to do that. The Thermal Desktop input table is going to have his entries with time, the sun vector, the planetary vector, which in planetary for us in this case is the moon, and then the ratio, which would be the altitude. The way I defined the coordinate system previously, the planetary vector, the planet would, or the moon would be below us at negative z direction. So the planetary vector is described as shown. The ratio, often just used if I'm going to put it essentially put an object essentially on the surface. I use a small number, just slightly greater than 1. This one might be a little bit this one might be a little bit above the surface, given that the radius of the moon is about 1736 kilometers, but But if you want to put it right on the ratio should probably match the altitude that you put in, but I put it into the ephemeris. And this one's a little bit different than I think I pulled an example out. It's a little bit different than what I showed in the ephemeris input. I had an 85 degree south latitude, and this one's for 90 degrees south. So you saw a plot like this earlier from the presentation this morning. This shows the what the solar elevation angle looks like from the ephemeris for 3 different southerly latitudes. I might just point out a couple of different things. I think before I mentioned the twilight, how I showed the sun setting above and below the horizon and the twilight setting. At the South Pole, if you put in an altitude above the surface, then your sunlight portion of the trajectory moves down, because you can if you have a height above the surface, you can actually see a negative sun angle. So that's how this would show. If I put in an altitude, I would be able to see, or if this was at altitude, I would be able to see below the horizon and would have a much a longer sunlit period. And I'd also noticed that I don't think I mentioned previously you see a little bumpiness in the curves especially for the 90 degree vector list, and maybe see a little bit for the 89 degree. I think that's due to the libration, the longitudinal libration of the moon. That happens on the longitudinal libration would happen over a synodic month, and that's what you're seeing there is a little bit of variation due to that. I'll point out that the JPL ephemeris is supposed to account for libration effects, so you don't need to worry about any of that as an input to your thermal desktop models or thermal models. If you develop a vector list from the JPL ephemeris, the libration will be included. I was going to. This is just a calculation for solar occultation. If you take the sun's apparent angular diameter of 0.53 degrees, you can calculate the solar occultation above and below the horizon. You see that this is based as an area fraction of the visible solar disk versus the horizon, the H over D. Assuming that the solar flux would be proportional to the percent visible in the sun disk, there's two ways to compute that, either with H over D or using, I think more conveniently, would be to use the elevation angle and the angular diameter as shown in the calculation below. This might be useful if you're doing some more manual or hand calculations. I believe that with the subtended angle option in Thermal Desktop that it would calculate this for you, but I haven't confirmed that. I was going to show one kind of interesting or unique application I alluded to this morning is for perpetually shaded regions of lunar polar craters. They, as I indicated before, that they may experience a non-negligible thermal radiation and reflected solar radiance from the Earth, as well as internal ground flow. The peak broadband Earthshine may exceed 150 milliwatts per square meter per the reference below. The hemispherical Earthshine at the lunar surface may be approximated with the equation. You have the radius of the Earth over just an inverse square law over the distance between the Earth and the Moon. S sub O is the solar flux, A is the Earth's albedo, and then Y, that's the tricky parameter. Y is the fraction of the illuminated Earth disk, which is would be if the Earth was fully visible, it'd be 100%, and then less if you can only see part of the Earth. T is the black of the Earth, and theta A and theta S are the solar elevation angle, and then if you want to introduce a local solar a local surface inclination, that's theta sub S. What's interesting is in all those parameters in JPL it's possible to obtain the Earth elevation angle unobstructed by local terrain and the fraction of the Earth's disk illuminated by the sun. So that's even in the ephemeris. So if you follow the process I demonstrated for the solar elevation angle, if you set the target to Earth and then specify 10, option 10, illuminated fraction in the observer table, it will tell you what fraction of the Earth's disk is illuminated or visible to you on the lunar surface, and then that ratio can be used to generate the flux due to Earthshine. The Earth elevation angle and the fraction of the Earth's disk illuminated by the sun are shown below. So the elevation angle varies between 7 degrees and just under -6 degrees at the 85 degree north latitude location. Much like the sun, the Earth will set below the horizon as indicated by a negative elevation angle. The ephemeris calculation of the illuminated fraction of the Earth's disk does not account for blockage by the observer body. If the Earth is set below the horizon, it's not visible on the moon, regardless of the illuminated fraction. Obviously, if it's not there, it's not there. So if you convert the illuminated fraction in the elevation angle, you can get a typical yearly elevation of Earthshine for a lunar location at 85 degrees north with a surface tilt of 15 degrees, and that's what's shown. The flux is, as I said, was 0 when the Earth sits below the horizon, and so there's a variation for planetary planet shine from the Earth as well as albedo from the Earth, and the two added together would be the total flux on a perpetually shaded region inside of a lunar crater. So that's just a little bit of a example to show how you can maybe extend the ephemeris to another application. Okay, this is a short presentation on shadowing and terrain effects. I'm going to talk about some calculations for shadowing by terrain features. A simple geometry can be used to predict if a surface feature shadows a target location. If the surface feature is near the target location, the moon's curvature may be neglected. But if it's going to show in the next slide, if the surface feature is very tall and far away, then you do have to consider the moon's curvature. The shadow length from a boulder of height h can be calculated as shown below, where alpha is the solar elevation angle. You can also calculate the height of the shaded region a distance x away from the boulder, but by using similar triangles. So you use some trigonometry to get the shadow length, and then the height of the shadow through similar triangles. If this is useful for several applications. If you have an object near a lander or near as indicated, a surface feature like a boulder, you can ascertain whether you're in the shadow. And I think that some of the folks that do some topographic measurements from time to time look at the length of a shadow to try to determine the height of a surface feature. The next case is to look at shadowing by terrain features, and Lisa Erickson developed this or derived these formulas here to determine this shadowing, and I'm just going to go through them. If the surface feature is large and very far away from the target location, then the moon's curvature can't be neglected. The moon's curvature will effectively reduce the height of the surface feature with respect to the target location, and you can kind of see that illustrated below. If you look at a surface feature that is h tall at this location ph, with the target location at point P, a flat ground, if you extend the flat ground plane from P in all directions, you can see it here horizontally. The effective height of the feature that shades P's ground plane is h sub f. That's highlighted here in green, and is calculated using the following series of equations. So Lisa derived these equations so you can get the distance of the effective height from the surface feature x, and you can get the value z through trigonometry, solve for z, and then you can do the same sort of thing with trigonometry to get the height from pH to your mythical ground plane for point P, and then use some just addition and subtraction to get the effective height of the surface feature cast in the shadow. And then through similar triangles, similarly like before, you can get the height of the shadow at the surface P, at the point P. If y is less than 0, then P is not shaded by the surface feature. So that's a good way to determine how to whether you're actually shaded or not. And Lisa makes the observation also that it's important to note that since the sunlight is imperfectly collimated, plus or minus 5 degrees, this estimate can be improved by checking for shadowing over a range of elevation angles. So if you're looking at a particular elevation angle, you can take that plus or minus 0.5 degrees to consider the effect of imperfect collimation. Another interesting problem is shading of equipment around lunar surface assets, and this was a little bit different for the Apollo missions. But if you look at a constraint that they had, they could not park the LRV in the lunar shadow longer than 2 hours to prevent low temperature damage to the electronics and the control and display console on the LRV. So they had to look at what shadow that the lunar module cast, and then where they could effectively park the Lunar Rover, and had a lot of talk with Ron Creel, who's I think attending today. He's had a lot of conversations with Ron about this, and he worked on the Lunar Rover back for the Apollo missions, and told me about some of the computational work they were doing back then to make these predictions. If you look at our situation, like at the South Pole with a lunar habitat, it's a little bit different with the well, not really different, but we're still being shaded, but we have a sun angle that's changing with azimuth, and so if we park an equipment in the shadow, we can potentially be in full shadow for a period of time. So we derive this particular relation to determine how long we are in full shadow based upon the diameter of something like a habitat or a lander, and the diameter of some equipment, and the distance between the equipment and the habitat. The 29.5 number is days in the length of the synodic lunar month. And so if you compute the time in full shadow, you can derive that as shown below, based upon capital D, which is the diameter of the large surface asset. Little d is the diameter of the equipment, and r is the distance between them. So this would give you a rough idea of what the time in full shadow would be. One thing that you should do is to check the length of the shadow per LTAG 9.3.2, and those are basically the relations that I just went through. The sun angle is generally so low at the poles is that if you're anywhere relatively close to the surface asset, you're going to be in the shadow, but you should still check it to make sure that you're not beyond the shadow. But if the sun's elevated at 1.5 degrees or less, or near horizontal, then it's going to cast a fairly long shadow. One other consideration is far-field terrain effects. The effects of far-field lunar terrain with the potential to shadow or re-radiate onto a site of interest may be included in a lunar thermal surface models via a projection technique. The far-field terrain may be projected onto boundary elements around the perimeter of the local surface model. The authors below demonstrated this approach for the Lunar 27 lander mission. The landing site was modeled as a 30-meter radius disk with the lander positioned at the center. They were concerned that several mountains in the region may shadow or radiate onto the lander, and they led to the approach illustrated below, where they used vertical elements on the perimeter to represent surface features some 20 to 30 kilometers away. The analysis showed the effect of the local mountains to be negligible in this case, but the approach may be useful for scenarios where it's not possible to extend a local mesh to account for far-field terrain. And I think and we may show some other cases where it may not be negligible. There's also an effort. I've worked with a few other authors on an effort to employ a similar technique to develop a projection of a far-field terrain onto a two-dimensional plane for shadowing considerations. We didn't really look at re-radiation. Far-field geographical features within large data sets may be reduced to two angles relative to a target location, to two angles elevation out and azimuth. If you can determine the blocking, what's actually being blocked as elevation at a particular azimuth angle, you can plot the blocking terrain or project it onto a 2D map as shown. If you use the ephemeris, you can also plot typical monthly sun tracks superimposed on the projected lunar terrain as shown at the bottom. So this could give you a very useful approach to try to determine eclipse periods as well as the effect of shadowing by local terrain or far-field terrain. Excuse me. The reference point in this case was for a lunar south pole at the 0-meter elevation relative to the mean lunar radius.
So like Carlos said, this section is about creating lunar surface models where the geometry of the ground reflects the topography of the terrain in a particular area. So this section is going to cover an approach to how to do this, and then at the end it's going to show some examples that take this approach. And in the middle I'm going to show a video that helps explain how to create the lunar surface mesh. So the lunar surface models where we represent the actual topography of the terrain model the ground with a finite element mesh. And to create these meshes, we use digital elevation models of the lunar surface, or DEMs. So a DEM of the moon gives us an image that looks like this here, where each block specifies the average elevation of a particular square that's bounded by constant latitude and longitude lines. Typically, you see DEMs represented with these 2D maps, and this is a DEM projected onto a 2D XY map, where the each pixel here gives you the elevation at a particular point. The elevations are determined based on measurements obtained from the Lunar Reconnaissance Orbiter's Lunar Orbiter Laser Altimeter instrument, and images like this, and the files that go with this that contain the actual elevations at the XY points are official gridded data records that are provided by the LRO LOLA team and are publicly available. So where can you find these DEMs such that you can download them and use them? I'm going to show two websites that you can go to. The first is the frequently asked questions page about LOLA data. they give you a link to the gridded data records, and that brings you to where the DEMs are available. It gives you two options, the cylindrical and polar. What they are is they specify the type of map projection used to project the DEM onto a 2D plane. I'm going to be talking about the polar map projections because that's what's used at the South Pole. And then once you click on that, it'll give you an option of what file type you're interested in, and this describes basically how the file is compressed. I'll be using the float image file format. Once you click on that, you'll see the list of DEMs available. Alternatively, you can get DEMs from the Lunar Orbiter Data Explorer webpage. This webpage is also used to get other types of LRO data products. You could search for them directly, or you can navigate to them using the dataset browser. Using this process here, which I'll flip through really quick. And since these slides will be available later, you'll have this as a future reference. Again, you get to the cylindrical and polar option, and then you can choose the file type that you're interested in. Once you do that, it'll bring up a web page that looks like this, that lists all the available DEMs that you can look at. If you select a LBL file with the same name as the DEM file, well, actually, if you select this view product, it'll bring up another page that shows you the heat map plot, and that gives you a visual description of the DEM, which is useful. Once you create your mesh, you can compare to it. This, again, is the actual DEM that you'll download. This LBL file contains information that's specific to the DEM, so it's useful for when you're reading the data. Some of the information included in it will be the scale. So this is a 5 meter per pixel, which means each pixel corresponds to a 5 meter by 5 meter block on the moon. This is a file right here that describes the polar map projection and information for parsing the DEM once you download it. So once you have a DEM, then the next step is to create the surface mesh. So there's multiple ways you can do this, but the approach that I'm going to talk about has two steps. The first thing that I do is to create a point cloud. I do that in Python, where each point in the point cloud corresponds to an elevation that's specified from the DEM. And even though the DEMs are coarse, this approach is sufficient if you use a sufficiently not coarse enough DEM. The next step is to take the point cloud and use it to create a triangular mesh with a meshing software. I use MeshLab because it is a software that is freely available. Okay, now once you have the DEM, the first thing you need to do to create the point cloud is you need to read it. This kind of really digs into the details, but I'll give you a high level overview of what's happening here. This code is available in the HLS Lunar Thermal Analysis Guidebook in the appendix. It's a sample Python code for reading the DEM. Again, if you look at the LBL file and the PolarCat file, that contains all the information that's needed. Because I'm using ones that are based on floats, when you uncompress the file, it's using a float format. So the first step here is unpacking the data. And when you do that, the data that's read is really a really long list of elevations, and then the index in that list is used to determine the X and Y coordinate on that 2D map. That's the DEM projected on the 2D plane. And once you have that, you use that to calculate the latitude and longitude, and the equation for doing that is in this, and it's different based on if you're at the South Pole or the North Pole. And then using the elevation, you can calculate the distance that that point is from the center of the moon when you add it to the radius of the moon. Once you have the longitude and the distance of the point from the center of the moon, those are the cylindrical coordinates. Then you can convert that to Cartesian coordinates using the standard cylindrical to Cartesian coordinate conversion. and that gives you your specific point in a point cloud. By doing this, we're able to create the point cloud that accounts for the curvature of the moon, where if we just did a straight up reading of the 2D DAM projected onto that 2D map, then you wouldn't be able to count for the curvature of the moon. Okay, so now here is the picture of the code that I showed before that has the conversion from spherical to Cartesian coordinates included. It also includes this section in the box that is made where it's a bunch of conditional statements that prevent you from outputting the entire DAM, and instead it'll only print out the DAM for a particular region. And I determined these X and Y points to bound what I'm outputting ahead of time by converting latitude and longitudes of particular points to X and Y points. And when you're outputting your XY points to create a point cloud file, you can use the format that's shown here, where it's just each point per line and it's space delimited, and then you write with an XYZ file extension. When you do that and you open it in a software like MeshLab, it'll show you all the points in the point cloud. So here is an example of a point cloud created from a 40-meter DAM. So each square in the DAM corresponds to an average elevation for a 40-meter by 40-meter section. This is for a south section of the South Pole on the moon, and because of that, we're actually viewing the underneath surface of the moon. To view this such that you're getting a view that matches that 2D heat map, you need to rotate this 180 degrees into the screen, and then 90 degrees clockwise. And then also, to make it so you can view the points, you need to click on this dot decorator button. And that's just how things are in MeshLab. So when I rotate the point cloud, as I described in the previous slide, then I get this image that matches the 2D map, but you can see how it has a little bit of a curvature to it. Then you can also see at the lower elevations how the points appear a little bit darker and further away than the points at the higher elevations. Okay, so once you have the point cloud, the next step is to create the surface mesh. So I'm gonna actually skip over this slide and the slide after it because it's gonna be covered in the video demo that I'm gonna show in a minute. But I'm gonna point out one quick thing first before I hop into the demo video. Oftentimes, if you're gonna create a mesh of a large section of terrain, you might end up with something like this, which is very large and would probably take a very long time for Thermal Desktop to run. So you might need to selectively reduce a mesh, particularly if you want a certain area to be more detailed. If you do that, and you're doing this in MeshLab, the easiest approach is to select a region like this, reduce the number of faces, then select a region it's a little bit smaller, reduce the number of faces, and continue to do that. And when you do that, you get a little bit more of this gradual mesh size element increase. Okay, so now it's time to go to the demo. So I'm gonna have to bring this over here. Pop this here, and can you guys see the screen?
Yeah, I see it.
Okay. This is an example of creating a lunar surface mesh from a point cloud. In our example, we're looking at the area around this point in the moon that's bounded by this box. The area is approximately 240 meters by 352 meters. I've already created a point cloud from a 5-meter digital elevation model of the lunar surface that's bounded within this area. Here's the point cloud that you see when first opening it in MeshLab. To open it, I went to File, Import Mesh, then selected my XYZ file. If you look over here, you can see the file name. And if you click on this eye, you can toggle the point cloud's visibility. Since this is an area on the South Pole and MeshLab's default view has the positive Z-axis pointing out of the screen, we're actually looking at the inside surface of the moon. So to adjust the orientation to match what you'd see in the Lunar Quick Map website or a picture of a digital elevation model, we need to change the orientation by flipping this 180 degrees and then flip this 90 degrees. And then to make it easier to see, I often click this dot decorator button. And here you can see the roughness of the terrain. To create a mesh, we first need to compute the normal vectors of the mesh vertices. To do this, we're going to go to Filters, Point Set, and Compute Normals for point sets. Then click Apply. In this example, I'm going to create surface meshes in two ways. The first way, I'm going to use the Screen-Poisson surface reconstruction method, and the second one, I'm going to use the ball pivoting method. To do the Screen-Poisson surface reconstruction method, we go to Filters, Remeshing Simplification Reconstruction, and Screen-Poisson. I'm going to use the default options, but if you have a large area, you may want to consider increasing the reconstruction depth to lower the amount of elements created. Here's the resulting mesh. If I click this button, you can see the outlines of the mesh elements. Note that the Screen-Poisson surface reconstruction method creates extra surfaces to result in a more square image, but we can easily remove them. To do this, we'll go to Filters and Selection, and we're going to select faces with edges longer than a certain length. And here I'm going to set it to 10, and then click Apply, and we see we have these larger surfaces selected, and now we can delete them. Now we have these remaining isolated surfaces, so we can remove these by going to Filters, Cleaning and Repairing, and remove isolated pieces. Now, if there's any other surfaces you'd like to delete, you can click on the selection button, select them, and then also delete. Next, I'll create a mesh using the ball pivoting method. Going to Filters, Remeshing Simplification Reconstruction, and ball pivoting. So I'm going to adjust these settings and then click Apply. And by adjusting these settings, it really controls the size of the mesh elements that are going to be created. So here's the resulting mesh. I can hide the points from the point cloud by clicking this button. And now let's say you want to increase the density of the mesh in a particular area, such as the area where your vehicle might be placed. So I'm going to zoom in on a particular spot, and then I'm going to highlight a number of cells. Okay, now I'm going to go to Filters, Remeshing Simplification and Reconstruction, and I'm going to go to Subdivision Surfaces Midpoint. This works really well for this type of mesh. And I'll start with applying the default method. Now, if I want to increase this a little bit more, a good way to do it is to do this gradually. I'll highlight more of these surfaces. And then repeat the same procedure. But now I'm going to change the edge threshold and apply that. And there we go. We have a more dense mesh, and I can measure the length of the elements to be 1.3 meters. On the other hand, if you had wanted to simplify a mesh, which is what you would want to do if you have too many mesh elements and you need to remove some of them, there are several options. The first is this clustering dissemination method. It's good at creating a nice pretty mesh. However, it only applies to the entire surface. So it's basically only useful if you created an entire mesh that is too detailed and you want to make the entire mesh less detailed. I'm going to close that. Now, if you just wanted to simplify a section of the mesh, you can do that by selecting some elements and then using the quadratic edge collapse dissemination method. And the program automatically gives you a default target number of faces. I typically use these, and then will gradually decrease these number of faces by applying this method more than once if this target number of faces is higher than what I'd like. But here's the example, reduced mesh. Another helpful thing that you can do is if you want to know what a particular point is on the surface, you can click this pick point and right click and get a point. And then you can actually save this point and open up a file, and it will give you the XYZ coordinates. Then you can take this XYZ coordinates and convert them to latitude and longitude. You can also look at the format of the save file and use it to construct your own, and then load points from that file and then use those to mark out a specific region that you're interested in. Lastly, if you want to export a mesh, you can go to File and Export Mesh As, and you can select which mesh you want to export. Now, make sure that you're selecting the mesh you want to. See, this is selecting the screen posts on mesh, not the ball pivoting mesh. So I'm going to select the ball pivoting mesh and then choose to export it in an STL format. And that's it. This is an example. Okay, so that is the video, and you guys can still hear me, correct?
Yep, we can hear you, Lisa.
Okay, thank you. I couldn't see the chat when this is going on, so just double checking. Okay, so now I'm going to go from the current slide. So once you have a mesh, the next thing to do is to bring it into Thermal Desktop. And again, there's multiple ways to do it, but the approach that I'm going to talk about in the next few slides has three main parts. The first is to take the STL file and then create a file that contains all of the points for each of the edges of the triangular elements. And then once I have that, I'll have a VBO script in AutoCAD that reads that file and then recreates the mesh. And once that's done, then the next step in Thermal Desktop is to highlight the surface and then convert it to the finite element mesh and add the surface properties. This section of the section of the Human Landing System Thermal Analysis Guidebook that talks about this approach is shown here. So this is an image here of two mesh elements that were imported into AutoCAD as an example. Each element is described by three sets of points or vectors, where the vectors really just point towards each of the vertices or the corners of the mesh elements. I'm calling them vectors because that's what they're referred to in the NumPy STL Python package that I use for reading the STL file. So this triangle is described by the points 0, 0, 0, 1, 0, 0, and 1, 0, 1, and this one by 1, 0, 0, 1, 0, 1, and 1, 1, 0. And if you put these 2 points in a file like this, you can then have AutoCAD reproduce these elements. So again, I use the Python package numpy-stl in order to extract these points for the STL file of the lunar surface mesh that I just made. And this might be digging a little bit too deep into the details, but this is an example of the Python code for outputting those mesh vectors. The main steps, I'll highlight it. The first thing it does is it reads in the mesh. Then what it does is it iterates through these sets of vectors. So it iterates through these and these. Then the next thing it does is iterates through each of those individual 3 sets of points or 3 vectors that go with the points. It'll iterate through this, this, this. And once it does that, it'll print out these 3 points to a text file. Then once I have the text file, the next thing I need to do is read it into AutoCAD. In order to do this, I use the AutoCAD VBA module. It's a module that if you already have an AutoCAD license, you can just go to the AutoCAD website and download it. There's a specific VBA module for each AutoCAD version, so make sure you grab the right one. When you have that installed, then you can type VBA man into your command line and it'll pop up this box. And then to access the Visual Basic Editor, you just press this button. If you open a thermal desktop model or an AutoCAD model that already has VBA code in it and you have the VBA manager installed, it will show you this pop-up. And if you're going to want to use the code, then you want to click Enable Macros. So the Visual Basic Editor that pops up when you click this button will look like this, and to run the code, you're going to press this button. I'm not going to go into the exact code for calculating it. It is available in the appendix of the Human Landing System Thermal Analysis Guidebook, but the main feature of this code is it uses the AutoCAD Add 3D Face method. And this method lets you create a element, either triangular or a quad element, based on the corners of each of the elements. So if you want to create a triangle, then you just specify 3 points, and for the 4th input, you just add one of your points a second time. If you're going to do a quad element, then you specify each of the 4 points. And once you press play, you'll get something kind of like this, where if this is a zoomed out picture that shows how the lunar surface mesh compares to the scale of the moon compared to the origin and the North Pole. It puts it right where it should be on the moon, which is why it looks very small compared to the entire moon. So when you have that imported, then you just highlight the ground and you convert it to the finite element mesh using the thermal FDFEM network, then convert to AutoCAD surface to nodes elements method in thermal desktop. Here's a note that once you create it, if you somehow lose where your mesh is on the screen, you can just take one node and then show it, and that'll direct you to where you should zoom in on the screen in order to find the mesh. And when you create the mesh, use the properties that we described earlier. For modeling the subsurface, I also use insolation nodes that vary with depth in terms of discretization. So the first few layers are going to be pretty close together. Then as I get further away from the surface, the nodes start becoming further apart. Okay, so now that I have a surface, this is the mesh that I created in the video. The next thing you might want to do is to put an object on it. Because the ground is not flat, if you want your object to be parallel to the ground, then you might need to do some math in order to get it to be perfectly parallel to the ground. I've outlined 2 approaches here. The simple approach is to take your object, put it on an articulator. The articulator starts off as aligned to the default coordinate system. You take the articulator, put it at the center of the triangle. Then what you can do for that particular triangle that you want your surface to be parallel to, you calculate the normal vector of the triangle. You can do that by taking the cross product of the lines that just two of the lines that describe the triangle, and you use the right-hand rule to make sure that you're getting the normal vector that points out in the direction that you want. And then once you have that, you can calculate a point that's some distance away from that triangle center, and you can put a temporary node there. And then what you can do is you can just drag the z-axis of the articulator over to that temporary node and drop it there, and that just automatically handles rotating the vehicle to where you want it to be. And if you want to increase its height off the surface, you can then just add a plus z translation to that articulator. An alternate approach is to actually calculate the orientations around the X, Y, and Z axes to get the bottom of your object to align with the element itself. This involves more math, but it's useful approach if your object is moving on the ground and changes locations over time, so you can't just manually force your articulator to align with the normal vector of each element. So if you do this, I already determined the order of rotations that Thermal Desktop takes when applying the math for doing the rotations. So if you do the rotations in this order, it'll give you the orientation around the x-axis, y-axis, and z-axis that's needed to have the bottom of your surface align with the mesh element. Okay, and here's my example cylinder that's 1 meter above the terrain. It's 12 meters high and its radius is 4 meters. Here is the example results for a particular orbit. This is for the end time of the orbit, and when I ran this, I first initialized the ground by doing a 5-year run before doing this last 1-month orbit. It's good practice to first do a run where you initialized the ground in order to have good starting temperatures for your run when you're concerned for actually getting results. And the cylinder here is coated with Z93, assuming a 10% lunar dust coverage. Lunar dust coverage is discussed in the guidebook, but we're not talking about it today in the presentations. Now, the surface terrain that I've shown here is large enough according to the method that Brian talked about earlier, but if you're concerned about shading from far field terrain, which you may be if you're not just looking for hotspots, but you want to model the environment throughout the entire year, then this is not a large enough section of the ground being modeled. So following the math that Greg talked about earlier, I used the geometric method to check if the terrain features could shadow a point that we're located in. So I looked at these 9 points and determined these results where all of the points except for 3 could cause this point to be shaded. And some of the points would cause the point to be shaded for all of the elevation angles that this point would see in terms of the elevation angles of the sun, and some of them would only be shading the point part of the time. To show what the impact of including this far field terrain would be in the thermal model, I actually meshed the large terrain and then removed all the areas at the lower elevations that I didn't care about. And then I imported it into Thermal Desktop. And once I did that, I set the optical properties, well, I set it to be active equals none. I used the normal optical properties of regolith when I created the elements. And I set it to be active equals none, so it could just act as a reflector or blocker in the calculation, and Thermal Desktop wouldn't have to bother calculating the temperatures of the far field terrain. So here's the scale of the actual detailed terrain that we're modeling versus this large area. Oops. Okay, so here is the results. I'm showing the direct incident solar flux versus time and the sink temperature versus time for the cases where the blocking terrain, the far field terrain, is present, and the cases where it's not present. When it's not present, the main differences in sink temperatures occur when you have the far field terrain blocking the point that we're looking at. So that occurs at these areas and at these areas. Besides that, the sink temperatures are pretty similar between the two cases. Now, this slide shows the direct incident solar flux and the ground temperatures, or it shows the direct incident solar flux on the ground and the temperatures of the ground at 2 different times. The first time is one where the far field terrain does not shade the ground that we're looking at, and the second one is when the far field terrain does shade the ground that we're looking at. You can also see the shadowing effects of the cylinder on the terrain. The last topic that I have for this presentation is a comparison to diviner data that we did to see how well the 3D lunar surface modeling approach was. In this comparison, we looked at this particular region and we were given brightness temperatures, which is the brightness temperatures quantify the radiation coming from the moon, but oftentimes the brightness temperatures are a good reflection of the actual kinetic temperatures. So we got the brightness temperatures from Pierre Williams for this comparison date. Here is a plot showing the brightness temperatures for this whole section. And it has the shape because it's reflective of the orbits that the Lunar Reconnaissance Orbiter had when it took the measurements. Here is the point cloud that corresponds to the ground mesh that I created for this comparison, overlapping with the diviner points. It's just meant to show you where they overlap. And this is meant to show you how the point cloud compares to the elevations. This hill was included just because this area that's a lower lying region is impacted by the presence of this hill. Here is where the lunar surface mesh was imported into Thermal Desktop, and here is what the mesh looked like. The mesh was created from a 40 meter by 40 meter DAM using the screen Poisson surface method. And the dense region here has an element sizes of approximately 250 meters, which is on par with the granularity of the diviner brightness temperatures that we were given. In the comparison, I applied the orbits as a vector list using the method that Greg talked about earlier using JPL horizons. However, because I'm not modeling just a small flat piece of the moon based on a specific latitude and longitude, and JPL horizons is giving you output for your particular location, assuming that the z-axis is pointing up, I needed to get my environments with respect to the North Pole, and then in Thermal Desktop I had to translate it down, and then I actually had to apply a rotation to get it to match. If you got your orbits using something like SPICE or JPL's Web Geocalc tool that uses SPICE as a backend, you can get your sun incident vectors with respect to the center of the moon, and in that case you don't have to deal with this translation. I'm only showing the diviner comparison for this approach, but I did also run it versus the using an orbit generated from SPICE. In the comparison also, I supplied a time-varying solar flux into the orbit manager. You can determine the time-varying solar flux by first getting your varying distances between the moon to the sun throughout the orbit duration. And then once you have that, because the solar flux is proportional to the inverse square of the distance of the sun, if you have your solar flux already known at one distance from the sun, for example, the distance at 1 AU, then you can just use this ratio to determine your solar flux at the other distances from the sun. And I use the JPL's Web Geocalc tool in order to get the distances between the moon to the sun at the different times using these settings here. In the comparison, because the points in the thermal desktop model don't perfectly align with the diviner points, I use the map data to external model feature in order to interpolate the points that thermal desktop had to the points of the diviner locations and get predicted temperatures at those points. Then this is the feature shown here. This is the export to node info option that I used for just straight up exporting the temperatures and the points that thermal desktop had for the nodes that were modeled into thermal desktop. Here is the properties used for the comparison. They follow the properties that we discussed earlier, so I won't spend longer on this, except for showing that this is the depth versus density relationship in the model. I'm using an average density at each location. Here's the results of the temperatures predicted in thermal desktop. Here are the temperature predictions that were made by each node in the mesh. And then here are the temperatures that are obtained using the interpolation from the map to external data feature. And this is the results of the comparison. On the left, I have a plot that shows the diviner brightness temperatures minus the thermal desktop predicted temperatures. And on the right, I have a plot that shows the diviner brightness temperatures plotted against the thermal desktop brightness temperatures. Ideally, the results would all be along the straight line and have a perfect correlation of 1. This Pearson coefficient of 0.975 is considered to be good when comparing the results to results in literature by lunar science folks. So the hypothesis for the difference in the scatter here is due to the fact that these regions reflect the shadow sun boundaries on the surface, and there is likely a mismatch in the shadow boundaries that's happening from my coarser mesh resolution and my coarser DAM than the actual terrain itself. So Glasser and Glasser observed this effect in their work here. The red section in this plot is corresponding to that denser region of the mesh, and the green points correspond to all the points that were mapped to the diviner points that were not part of that dense region. In the diviner comparison, the last thing I'm going to talk about is the impact of different surface properties on the ground. So I repeated this comparison first with a model that used a different curve that gives you albedo versus incident angle. And then the second one, I repeated the comparison using a model that has a different thermal conductivity and density relationship. The results are shown here in terms of the comparison. These two are pretty close, but there's a bigger difference when the optical properties or the albedo is different. And this particular location gave me a worse comparison. Here are all the resulting temperatures. You can see that this one's colder than the other two, and just to give you an idea, this is the comparison of the curves of albedo for the different runs. This one is run using the FANG 2019 curve, and this one is from FANG's 2020 curve. So if you change your albedo, then you can change the results of your surface temperature, and then based on your analysis, you can determine how important that is. And that could be important for you because albedo depends on location, but it may not be, and you'll have to determine that.
100% copy-paste error, probably. Here in this planetary coordinate system, again, suggesting we try to use the subsolar one, but add a cosine of a lat minus long. It needs to be times a cosine of a long minus long for planetary and subsolar. It also needs to be times the cosine of the difference in the latitude degrees. So cosine times a cosine function as opposed to cosine times just a simple subtraction. Also, this assumes that your cosine function will take degree, because we have degrees here, inputs. So note that if your cosine 90 doesn't equal 0, you need to convert. That's on you. But so yeah, just a little bit of clarification here that it is a cosine difference times a cosine difference in those Latin long for the planetary coordinate system. That's really it.
Thanks, Brian.
Didn't know if there was time for if anybody else had any additional questions or.
There's a question here. It says, I'm wondering when exact surface topography around a lander or surface fission power reactor should be considered.
Like when you want to start actually including the topography?
Yeah.
If you know your landing site, then you can start seeing if you're going to have. So part of it has to do with, are you trying to survive the lunar night? If you're trying to survive the lunar night, then you're going to get information about the topography from people doing lighting analysis, and that'll tell you how much things are going to be in dark, and that'll account for the topography, some of that change in that ways. And if you're located, once you're done the initial, I think, sizing studies, you're going to probably want to start putting your surface on the terrain to see if there's any impact on the roughness of the terrain. But if you're going to be by a hill and you know you're going to be by a hill, you're going to probably want to start looking at that earlier. Greg and Brian, if you want to add to that.
Yeah. I think, I'm going to pull off of some statements that Greg's made in the past and some work that he did for all pair landing sites as well. But yes, and even polar, if you have a large geographical feature, a ridge or a mountain, there's no attenuation from distance, but depending upon, its view factor, the arc minutes or seconds that it is of your above horizon view, the effect can be significant of additional view factor to an illuminated ground surface. That's addressing the most recent question. The other, going back to when you need to consider it, I would just in general thermal analysis terms, right? You would try to envelope the question first, and if you had issues with upper lower temperature limits on components, then you start maybe sharpening the pencil. I wouldn't necessarily say go do a topographical analysis as your first order cut unless you needed it to show that to either minimize or maximize the effect of the surface, because you need that fidelity. If you can substitute it or envelope the conditions with a simpler analysis, that may be preferred. Again, these are trying to, the design standard for natural environments in the LTAG is, survivability of an asset on the surface. Can it be designed to meet, worst case conditions in that environment, not necessarily what is the exact temperature of that asset going to be. If that's helpful, or maybe that's even less clear. I don't know.
There's one other thing that I wanted to point out is that, and I don't know if this was in Carlos' section earlier, is typically if you're doing a flat plane model of the ground and you're at the South Pole, by the temperatures that you're going to get in Thermal Desktop aren't going to match necessarily the worst case temperatures that you see that's been recorded from the diviner temperature measurements. So you'll want to double check to see what those are. Carlos, did you talk about this in your sections?
I don't think Carlos addressed it specifically.
Okay.
One thing that you can do is, modeling just a simple flat plane, you can change its relative angle to, you can increase the effective solar incidence angle to match something along the, at a polar location. Whereas when you're more equatorial, you've got, you're more concerned about the sun directly overhead, subsolar points, and the solar incidence angle isn't as affected by maybe some of the, well, the solar incidence angle is affected just as much, but the received incident heat is not. Whereas on the, when you're closer to the pole, a small change in orientation of that ground plane can have a decently significant effect on the resolved surface temperature of that plane. So to worst case the temperature of your ground plane, you may try rotating it in relationship to the solar vector to worst case that surface temperature.
Yeah, that's an approach that I've done in the past. Just wanted to make sure that folks are aware of doing that.
Hey, sorry I couldn't respond. I couldn't find my unmute button once you share the screen. I'm not used to WebEx.
Oh, I get that.
Okay. Let me see if I have this. Share. All right. That's my screen?
Yes.
All right. So in summary, what did we cover? We covered the Earth's moon, lunar space and surface thermal environments, thermal physical and optical properties for lunar regolith, modeling lunar orbits, lunar surface ground plane modeling approaches. We showed a lunar surface ground plane example video. Greg showed the vector list, shading and blocking. Lunar surface, Lisa did a great job of showing us the lunar surface 3D terrain modeling approaches, in addition to the how to mesh 3D terrain example. What we didn't cover, and this is a product of the fact that we just didn't have enough time to do it, is we didn't cover the ascent-descent modeling. This focuses on modeling the mission trajectory from the surface to LLO. So either from the surface to LLO or LLO to the surface. We also didn't cover the lunar dust impacts, which can significantly impact the thermal analysis due to its contamination effects on your thermal optical properties on radiator surfaces. So, but you could find this information in the LTAG, which is a quick Google search. You could just type it in. You can type in Human Landing System Lunar Thermal Analysis Guidebook on Google, and it pops up, and you'll see the PDF right there. Now, updates. We do plan, the goal has been to make updates to LTAG. Every once in a while, when people are taking a deep dive into the document, they find errors or corrections, or there's things that we might want to add. But this would have to go through a change request process. So hopefully we could have a new revision out next year. Some things to expect that Lisa did cover in one of her slides, ice with lunar regolith, which is the bulk thermal conductivity calculations, which include regolith, ice, water vapor in between the voids. So that's something that we plan to add into the LTAG for the next revision. In addition, even during this presentation, there was an error that was caught, and it's a correction on this equation right here, which is on LTAG 4.3.1, and which Brian brought up. It's missing a cosine before this parentheses for the left, or the planetary lat and subsolar lat.
And Brian Evans had a great comment on worst case enveloping versus geoterrain effects comments. And then I guess a follow-on question, the 1.5 degree moon axis tilt angle. Correct me if I'm wrong, Greg, Lisa, others, but that's sort of like the Earth's angle, 22.5. It's just the axis of rotation difference from the ecliptic plane to the sun. So it's a 1.5 degree solar plus or minus solar variation up and down as the with the moon's axis tilt. So it's the seasonal change in the solar elevation angle.
That's right, Brian. It's relative to the ecliptic, just like the Earth tilt is, and it's just 1.54 degrees.
If you wanted the elevation angle at the particular point, then you would do the approach that Greg took, where you look at JPL horizons in order to get your elevation and azimuth angles versus time.
That's right. The one, if you wanted it for that particular time, or the
Yeah, if you wanted it for that particular point.
Yes.
yeah, the 1.5 is generally what we would do to envelope an environment, plus or minus that.
Yep.
All right, Jedediah, I think we're done.
Great. Thank you all for presenting all of that. It's very fascinating.